All right, let's continue our asset extraction from Eggerland. So where did we leave off? Yeah, we were decoding the pattern table, which had a separate function for some reason. But yeah, we do see some ANDing and some loops. So yeah, we'll figure this one out. So we can extract the composition of the sprites, which is mainly the thing I was looking at. Let's go look at this address here. All right. So I think this will load. Well, it loads now, but I just pressed spacebar, so we're going back to the menu. Yeah, I think I'll let it go back to the demo, and I'm assuming it's going to load as well, or break as well, which it does. And then we'll look at the pointer that contains the data, which is going to be in HL 8B97. So that's our target. Okay, that's still here. Okay, so this will be our target. Of course, we don't know how long it's going to be. What we do see, though, when we compare it to the previous algorithm, we did load the first 2 bytes as well and did some comparisons with that. So it looks like, hello, Kimberly. We did some comparisons with that. So that looks to be quite similar, but then it does diverge a bit here because we're ANDing and comparing immediately. I don't think we were doing that in the other function. Well, I mean, I assume they did, but yeah, sure. So let's see, we'll have to make a different function here in our C++ code because we're not dealing with, so I'm working on the same thing, except it's a different type of data. So I'm extracting the code that does that makes up the sprites. So the pixels that make up Lolo and all the enemies and whatever. So we see if we can extract those as well. Other than the artwork, like the big title here that we did last time. But yeah, there's apparently a different algorithm for the data contained in the sprites than there is for the general assets. So yeah, we have to write a different thing here. That's weird. Oh, that's my dump. Yeah, I was looking at this. So yeah, this is the algorithm we have to convert to C++ to get a grasp of it. So yeah, we're gonna have something similar like this. And this is going to be the pattern table, I assume. This might also be used for the color information, the color table, so we might have to rename that function. Of course, I already forgot the address here, 8B97. Right. Okay. Then we will have about the same thing. So we're going to do a buffer of 4 kilobytes. That should be enough, right? Well, I mean, it might not be, but that doesn't really matter. We'll just make the buffer bigger if it crashes or seg faults. So yeah, let's copy this. I have to clean this up later, but this is just a test now, right? So we're loading the ROM, we're skipping to the offset, and we're reading like data length amount of bytes, which is 4 kilobytes. So we have our buffer. And then we're pushing DE. DE contains C000, which contains our target writing thing, right? I have to look up what the EXX instruction did again, because I don't remember that by heart. So let's look at the reference. Opcode table for EXX. Okay, that's swap between BC and DE. And wait, what? Exchange this. Oh, BC, DE, and HL with their prime alternatives. Okay, that's interesting. So I don't know why exactly they're doing that at the beginning of this function. Because yeah, we're pushing DE. So, and at the end, what do we do here? We're popping BC. So we don't do any exchanges. I'm going to ignore this because it's probably irrelevant for the algorithm, right? So let's start with this one. So we're loading the first byte in C and the second byte in B. Okay, that looks quite similar to what we were doing for the artwork. Right, so that's again the prefixes, I assume. Okay. Then what is next? Push BC. Right, so that's okay. That's similar because we're saving the two first bytes of the algorithm on the stack. So this F8 and A0. Okay, so then we're loading the third byte, and we're adding it with C. How is that different? Okay, yeah, that is this. And we're subtracting prefix 2 over, yeah, we're comparing it with B. This is literally the same though. And we're jumping to 6 CDE. Is this a 1 repetition? CDE is this one? Yep, that's a 1 repetition. So how is this different? That's so weird. And then we're jumping to 6CD5, which is this part. Okay, so, and again, like this is literally the same thing though. Wait, am I looking at the correct function here? Yes, I am. So this is the old function, right? We already had that one. Yeah, this is exactly the same thing, right? We're loading the first two prefixes. We're adding the first or the third byte with one of the prefixes and subtracting the other. If it's true or non-zero, then we do a 1 length. Yeah, and then the loop goes back over here. This is, oh, it's writing out. It's not looping, right? It's not loop. It's just writing out the target data. We did the same here. So we were jumping here, right? 6 CDE. We're jumping here, and we're jumping then back to CD5, which does the writing out. Okay, so that's exactly the same. Increasing AHL to the next byte, popping BC. Okay. Oh, and then we're jumping to the start of the thing again. This is literally the same thing as we were seeing in the other algorithm though. So maybe they re-implemented it twice, or they did something else in this section here. So this is pretty much the same, right? And then we have to look at the exit condition. Like this is the exit condition, and then the multi-repetition, maybe that's different. So let's take a look at that. Or well, in fact, we can take a look at the exit condition first. So yeah, loading the third byte, adding it with prefix 1, subtracting prefix 2, and jumping if it's whatever, non-zero. That's a 1 repetition. Then we're loading C into A, and the CPL is the inversion, right? Yeah, that's bit bit inversion. So again, exactly the same as we did yesterday, or the last time we did this. Yeah, that's this CPL here, right? And we're ANDing it with HL, which is the 4th byte then, because we incremented, yeah, we incremented HL here. Oh wait, no, we didn't. Is that the same? Oh, we're decrementing and ANDing. That's interesting. So in the artwork algorithm, we do decrement HL, so we are ANDing it here with the previous byte. And we're incrementing HL here, so we're skipping forward to the next one here. Well, no, wait. This is the return condition. I have to make sure that I don't make a mistake here. So this is a return condition, right? So yeah, we load the 3rd byte, ANDing it, subtracting B, and jumping. That's the 1 repetition exception, and then this is the return condition, right? The exit condition, which increases HL. And then the accumulator at this point, right? So yeah. Okay, we're comparing the two bytes that are next to each other. Okay, and is this the same? So we're increasing, comparing what it's pointing to. Where are we? Here. Yeah. No, our exit condition is different, or there is none. I don't see a return here. That's pretty strange. Yeah, we don't have any there aren't any there is no return here. That's interesting. So yeah, because here we go to 6CDE, which is the single repetition condition, and then we immediately go to processing the bytes, and that would be exactly the same as the old algorithm, I think. Yeah. So this part is just omitted. Yeah, this part is the exit condition. So what we're doing in the algorithm itself is loading C into A, inverting, subtracting HL, and ANDing. Wait, can I split this thing? I don't really do that often. So we're looking at, that's the exit condition, right? So this is the processing of the multi-repetition routine with the loop here, increasing, popping, and jumping back. Okay, so that's the body of the, well, including the writing to the output buffer. So we have our one condition here, and the algorithm starts here then. The same algorithm, yeah, that looks the same, right? So we're decreasing here. Yeah, we're not decreasing the HL pointer here for some reason. We're testing bit 0 in the prefix. That's for this rotate, right? You know, we have seen that. Okay, and then here it diverges to, we're comparing it with hard-coded 2. Okay. And this exception is just the rotate, right? So that's fine. But instead of adding 3 to A, we're comparing it to 2, and then we're increasing. Okay, so we're doing stuff differently though. but then we are matching up again, loading A into B, HL into A to D, increasing DE. Okay, and then we have the regular writing routine. Yeah, that's the exact same. So there is some stuff here. So where in the artwork we had a base of 3, right? If we do multiple repetitions, we have a minimum of 3 because we're adding 3 to our repetition count all the time, and we're not doing this here. So I think we can assume that that the exit part is, this part is gone, right? We do have this, which is exactly the same. I don't think we need the repetition count set variable anymore because that was only because of this pre-exit condition that doesn't exist anymore in that specific algorithm. Yeah, because we can just do if it's this, otherwise we can do, if it's like 1 we do this, and otherwise we do that, right? So I don't think we need that anymore. Yeah, so I think we can just do this. Okay, we need some repetition count, current value. I guess we have to keep track of all of these, right? And then we have to start at this position. And that has to be in the while loop, of course, so that makes sense too. Yeah, of course. And where is our break condition then, though? How do we exit here? So we have to jump to 6CE9, perhaps, which we don't anywhere. Yeah, that's weird. How do we exit out of this function? So we have our loop. This is our writing loop. We're jumping back to 6CC0, which is all the way at the top. That's the one condition. Okay, and is it, oh, it's 6CE2. Okay. Oh, this is, we're jumping here based on the carry flag. Okay, sure. We're testing A for 0. If it's non-zero, okay, if it's non-zero, we jump back up, I assume. Wait, no, oh, we're going beyond here. I didn't copy this part. Okay. That's interesting. I thought the function stopped here, but apparently it doesn't. Oh, and here are our exchanges. We're adding 4 times the HL, or incrementing 4 times. So how far does this go, though? Does it go all the way here? Yeah, because we are jumping to 6CEB here, beyond this return. So this return is reached if this condition here fails, right? Where is it? Yeah, this tests A for 0. If it is 0, well, if it is non-zero, we jump outside of the function. If it is 0, we continue. We're loading HL into B, incrementing B, testing again B. Okay, sure. Same thing. That mustn't be, or that must be 0 to return. Okay, so we're doing 2 tests based on the current contents of A and B, and that exits our function. But then, if that's not the case, then we do a whole other piece of code here. So our LDIR is block copy, right? So I have to look up the things again here. LDIR is from HL to DE, both incremented, and B is a counter. BC or B? Yeah, BC. So from HL to DE. Okay, so 8 bytes are being copied here, which would make sense because if we were looking at the name table, those are, or the pattern table, those are indeed 8 bytes long per pattern, right? Yeah, that does make sense. I do wonder which return we're going to hit in this function, or at least with this set of data that we have here at 8B97. So let's put a breakpoint there and see which one we hit. That'll make it easier to see which path we take within this function, right? So we have a return here, and then we have a return all the way down here, 62.9, that's correct, right? So we have the first one, yeah, 6CEA and 62.9. Yeah, so I'm going to let it run. And at that point, I'm going to look at C000 again to see what we're actually decoding here. So we're stopping at 6CEA, which is the first one. So these tests fail. So this ANDing and this test of B fails. And then we are returning early. So we're not handling this part of the function, which is fine. So we have to find like a piece of data that does trigger that function, if it's interesting enough, of course. Because if we are extracting like all the sprite data, then that might suffice. That might be enough. So we don't necessarily have to decode all this bottom stuff. So let's look at C000. I'm going to open a new window. Which is already at C000 again, and those look like the sprites for the game, right? So if you look at the tile viewer here, we do see that, for example, sprite pattern 0 is all blank, which is these 8 zeros here. So if I put some ones in there, like for example, if I want to paint the right side white or whatever color is defined, I can put OF in all the rows because it's 1 byte per row. So that should paint half the thing, half the pattern. The right side of the pattern should be colored now. For pattern 0, once I continue here. I don't think the colors are defined right well. Oh, we can see that, right? is it 800? I think it might be C800 might be the end of that thing. That would be 2 kilobytes, I think. Yeah, I guess it's until here. Okay, let's double check. Yeah, so the right side of that first pattern is now filled in with color. So we are looking at, oh wait, it did break again, but we could be loading a different section of data though. So what does it, yeah, okay, this is the color table. Okay, sure, the color table does go into the bottom section of that function. That's good. So this has a different source pointer, right? So this is not the data at 8b97, which contains the name, the pattern table. Now this is the color table. So if we change this to F4, 4 is blue, I think. So I think the pattern should turn blue now. The right side, or its inverse. I don't know that by heart. Yeah, so it's the other side. Okay, sure. So it's one of the two colors, right? So either the black or the white gets replaced by the color that I put there. So I should have put 4F, I guess, or 40. Right. So yeah, that one does indeed use the bottom part of that function. But that's fine. We can start with the pattern table and then later do the color table. Because we do need the colors as well, if we want to extract all the assets, of course. Okay, we do have some more patterns being loaded, because we're again stopping at the first return. I don't know. So this looks again like a pattern table. I'm going to let it overwrite and see if it overwrites my first pattern here. Because then they would be doing the same thing twice, and I don't know why they would do that. Yeah. That's strange. So my pattern did get overwritten here. And then again the colors, black again of course, because I didn't change it. And again. Really? Now it's different information though. And again, so yeah, I don't know exactly what these pointers all do or what this data all represents, right? But we did seem to override our pattern table twice, which is weird, because why would you do that, right? That's interesting. In any case, we know that we exit early, so we don't have to implement the bottom part of the function, right? So if you go back here, we can assume that we're returning here. So that means we're never taking these jumps beyond this, because none of this function, part of the function below, jumps back to 6CEA or whatever, does it? Yeah, no, that's the down jump. 6007 is also within the last part. 6040. Okay, that's again beyond this function. That sucks. This is larger than I thought. Yes, this jumps all the way here. 6040. Again, beyond this function. So the function doesn't stop here either. So 29. Yeah. So this part is part of it as well. Where's my return? So this is also a conditional return, and it's halting here even now. I mean, we can fix that by just putting a, if we're porting that to C++, we can just fix that by typing a message if we do encounter that situation where we are jumping here to 6040 or whatever. Yeah, because over here we're jumping to 6D2A, which is the start of this one here. So this is definitely part of it. Now, this is a conditional return, I think, return M. So that implies that we can go beyond this. So return M if the sign flag is set. the top stack entry is popped into the PC, so meaning that we return to the top stack entry based on the sign flag. Okay, that makes it more complex, but this is a conditional return, which implies that we can fail here and just continue on. And then I'm seeing a halt here. That's weird. So I'm assuming the halt is the end of the function, like an unreachable part of the code or something wrong with the coding perhaps. Yeah, suspend CPU operation until an interrupt or reset occurs. I don't know if there's an interrupt that would be associated with loading this pattern table, though. It could be. I don't know the architecture well enough for that. Yeah, so let's ignore this part for now, because like I said, the decoding of the stuff we are interested in doesn't go beyond the first part until this first return. So this part is what we're going to do, of which we have quite a few parts already. So that also makes sense that we don't have an early exit condition, because that early exit condition, it doesn't exist here, where we have multiple paths in this larger function to exit. So that doesn't really matter. So where are we? We're testing bit 0 of C. Right, that's for the rotation to the right. Okay. Yeah, we do have that, right? That's right, where are we? No, we don't have the rotation yet, because that's here, right? So I'm going to copy this. This is going to be incorrect, right? So this is the second part of our thing here, and I'm going to copy the writing out into the data as well, because that happens all the time, right? That might need to be separated in a different function, but doesn't really matter. Let's just put it at the end here. But yeah, we have to output or write into the output, right? And then I'm going to put my dump function as well, so that I know what we're decoding. And this is, oh, I didn't put my while loop in, I guess. Yeah, because I don't have an, okay, right, I don't have a return condition. Oh, no, we do. So there is going to be a jump back up. So I can break based on the two conditions we saw, right? Yeah, so this return is reached if these two conditions are false. So we can test for those and then break out of the while loop, and then we're done. Yeah, but now it's an infinite loop as it stands now. Yes, asset extraction is indeed what we are doing. We're extracting the pixel makeup of all the game elements. That's what we're doing. Right, so it starts to diverge. So this is correct. I think this is identical to the first function, right? So let's double check. We are loading the third byte, adding it with the prefix 1 and subtracting prefix 2. So we're loading the third byte, which is the current byte, right? Well, not necessarily the hex, but I'm looking at the equivalent assembly, like the assembly equivalent of the hex code. But yes, it's like reverse engineering what the game is doing. So yeah, we're adding with prefix 1 and subtracting prefix 2, which is this. And HL contains the third byte here, but that would be progressing through the data, right? So that always gets incremented. So current data index, okay, that's incremented by 1. What do you mean where to start the dumping? I'm just using the OpenMSX debugger, right? So all the data is right here. I just exported it to a file, so I can easily look at it in VS Code. That's a little bit easier to navigate. So, wait, where are we here? Yeah, so loading the third byte or the current byte, adding it with the prefix 1, subtracting prefix 2, determine whether that's the case, non-zero, and then we're jumping to 6CDE, which is the 1 condition. So we're loading the for loop counter with 1 and writing out the data, right? So we're loading the pointer to the data, writing to DE, increasing DE, and jumping. Well, we're not jumping because it's 1, okay? Increasing to the next one, so we're doing an increment of 1, okay? And we're returning to the top of the function here. That sounds, I mean, extracting keys from TPMs, that sounds quite complex. I wouldn't really know where to start. Because that involves like hardware extraction, right? Like you have to like delete some ICs and stuff, I assume, or is that? Because you can't really, like, that's the point of the TPM, right? That you can't really extract the keys through normal means. All right, if you're using like a vulnerability or whatever in the instruction set, that sounds complex though, and it's also timing related, right? Where you have to do like certain timings and stuff to get some things to mess up. Yeah, that's interesting though. Like I've never attempted that. Yeah, that's what I figured. You have to probe the thing, get the oscilloscope out. But yeah, this is a little bit easier in the sense that we're looking at assembly that was written like in 1985 or 1984, like it's handwritten assembly. So yeah, that's a bit slightly different from what I'm doing here, but yeah, that's also quite interesting, of course. All right, so if we are not in the case where we have the 1 repetition, we're loading C into A, which is this thing here, right? So we're loading this and we're ANDing with the inverse of the prefix. So we're inverting the prefix, ANDing with the current byte, and increasing the byte with 1 thing. Yeah, I've never done these bounties things. I did look into it a little bit, but I've never like spent lots of time into an actual bounty. I mean, I looked through them and see there was something interesting, but yeah, I couldn't really find anything that caught my attention. That I said like that I want to figure out that thing. Like this is more for like not entertainment, but I mean, I do like this game, so that's more the goal that I'm trying to achieve here. Is like it's a game I like, and I just want to see how it works internally. But yeah, you do have to keep up with the new stuff. That's right. Right, so we do our bit check. That's this one, first bit in the prefix. That's the same, right? Yeah, first bit of prefix 1. If that's the case, we jump over. Right, I'm not on Windows though. It's been quite a while since I've done Windows stuff, but yeah. Right, so we're skipping the rotation based on bit 0 of prefix 1. Same thing exactly. And then we're comparing with 2. So here it starts to diverge from the original algorithm. So we're comparing with the hard-coded value of 2. And that's the accumulator, right? So the accumulator still contains, well, it contains the ANDed, like the bottom n bits ANDed with the current byte. The bottom n bits of the prefix 1, right? ANDed with the current value. Yeah, I do prefer like more stability. Like I'm running Linux all the time. I don't really reload my operating systems and stuff. Yeah, I do prefer the stability. Well, yeah, that's part of the deal, I guess. Unless you're doing everything in virtual machines and stuff. But yeah, that makes it sometimes more difficult as well. Right, so the value contains our, so this is already wrong, right? This is not what we're doing anymore. We're not adding 3. It's at this point that we are comparing to 2. And based on the carry flag, we're jumping to 6CE2, which is immediately the test for exits. Okay, that's interesting. So I don't know if this happens straight away. This must be the exit condition within the data, though. Yeah, so we're comparing with 2. So I'm assuming if it is, I have to look up when the carry flag is set. That's with an immediate, right? Yeah, with an immediate, which we don't have here. Yeah, CPN. Subtract n from a, so a minus 2, and the flag is set if it's below 0, I assume. Yeah, so if a minus 2 is smaller than 0, I think that's what that means. Then we do the exit condition, and a is at this point our current value, right? So we're not doing this either. We're not resetting the current value. We are incrementing our pointer to the next one, though. So the only thing we're doing here is this. Right. Instead of +2. And then yeah, it's the thing that's being ANDed we need. Where is that? Yeah. Oh, it is the repetition count still. Yeah, right, because that's the data and the current. So we're taking the bottom n bits based on the data here. Yeah, that's what prefix 1 defines, right? How many bits are used for the repetition count, and how many are used for settings or whatever, like a bit field. So it is this value that we're checking, right? So if repetition count minus 2 is smaller than 0, of course I'm using unsigned integers, so I might have to change that though. Yeah, just to be sure. And this is the exit condition. I'm going to break here, but this is missing our checks here, right? So instead of breaking here, we do have a couple checks because we are jumping to 6CE2, right? Based on this subtraction, we're basing, or we're jumping to 6CE2, and we're doing 2 more checks on the current value and on prefix 2, prefix 2, which is B. And then we return. So if either these are a success, we do jump to this other part of the function, which has some like other stuff going on that we don't know about, but we don't trigger in this data yet. Okay, but like we'll do that later. Actually, this happens before. Right, the rotation, I think it happens before the rotation even, but here's the rotation. No, the increment happens here. Also, no, I'm incrementing A, not HL. Wait, I must see that I don't make a mistake here. No, it's this one. It's this one I'm thinking of. Yeah, no. That happens before the bit test. Okay, sure. So technically we can put that here. Right, and then we do the bit test, rotating if so, checking whether it's -2 is larger than 0, and then we're increasing A. At this point, A contains prefix 1, right? Well, no, it's inverted. It's it's the ANDed version with the. Is the current byte ANDed with the inversion of prefix 1? That's the repetition count. Okay, so now it's added. Okay, so we are doing. Oops. We're incrementing our repetition count. That's the equivalent of like the +3, I think. Yeah, I mean, it is a help, but I try not to like involve that too much, because like that takes away a bit of the fun, I guess. And I mean, I can just copy paste this in whatever AI and just get a C++ equivalent out of it, or C equivalent out of it. But I mean, that's not really fun, right? So yeah, I do prefer to do that by hand and see where are the mistakes that I make. So yeah, I don't really mind doing that. Right, so we are putting our repetition count, increasing that by 1, incrementing it by 1. Okay, and then we are loading. Okay, and this is the write out routine, right? Yeah, we're loading the repetition count in our B register, writing what HL points to into the accumulator again, writing that out into DE. Okay, so that's it then. Also, this is not supposed to be here, I think. Wait, is it? No, so that's this increment A, right? That should be after the bit check. And then we have our, oh, no. Yeah, after the comparison with 2, or the subtraction of 2. Yeah, so that needs to come after. And then, yeah, and then we just exit, that's it. Yeah, I mean, you can do that indeed, but like there's, I mean, I do enjoy looking at it myself. Yeah. I mean, you can achieve quite a bit though, that's true. Like if you want to make changes and stuff. Yeah, for sure. Okay, so I don't know how this is going to go, but let's see if we can get something interesting out of this. I have to get my thing here again. Okay, we're just exiting, so we're doing nothing here. I don't think that's the case though for this data. Well, at least we're exiting, right? Let's see. Just write some messages here so we can see where we are. So we do have a repetition count of 0. Meaning, so we have to output what inputs we are dealing with. And then let's put that in hex. And then the prefix. Might have to format these better, both 0. That's impossible. Because if we're looking at yeah, I don't know if I'm reading stuff here correctly. I mean, it should though. Right, that makes sense. You mean 16 gigs of video RAM, or? As in when you're loading your LLM, right? Because I have a very small video card in this one, a very old one. So I can't really run much locally anyway. Oh, okay, right. Makes sense. What am I missing here? Data. Oh, of course. That's a stupid mistake. I need to add 4,000, right? Or subtract 4,000. Well, I mean, that would make it 4, I guess. But let's double check. Okay, so that's a good sign. We at least have 8 zeros, which is correct. Which model are you running? Because there's so much choice these days. 3, 6, oh, it's nine zeros. Which does make sense too, because we do have more than 8 in the first line. There's like 2 sets of 8 zeros, right? But yeah. But we do encounter a repetition count of 0, though. Which we increment to 1. Okay. Oh, is our while loop not satisfied? I guess this happens too early, though. Right. I haven't seen the dolphin results yet. Yeah, I should look some more into it, but I haven't gotten time to invest much in the AI stuff. Yeah, this is wrong, right? Where are we? Yeah, it is this comparison, right? That's not correct. So I mean, the stupid thing is it doesn't explain when the carry flag gets set here. When I maybe I can look at a different compare, it says. So that doesn't give us any information. C as defined, so carry as defined. Subtracts n from A and affects the flags according to the result. A is not modified. Okay, so we are going to break on that in the game and see what it does with the data here. So we're starting with A7, which is correct, right? Yeah, A7 is like the 3rd byte. Prefix is F8, that's also correct. Okay, so Repka, okay, we did one iteration with 7, and then we have one repetition of 1. Okay, that does make sense. Yes, I do know in the sense that these are standard, well, at least the thing I'm doing now, right? Wait, let me continue and I'll show you. Like they're not really images in the same sense as we know images to be here. So I'm trying to extract this main menu here, main screen, like the Eggerland logo and the mystery text. And how that works is, so you have the tile viewer here. These are the tiles that are defined in memory, right? And they are composed by reference, right? So you have a pattern reference in each of these columns and rows. So I've been able to extract this this data as in the makeup of the sequence of patterns. And what I'm trying to do now is to do the patterns themselves. In other words, these the composition of the things themselves. And of course, because you're working with such an old machine, like they did it the way that machine expected the data to be, right? So for example, we can see that here, right? So if we go to the first breakpoint, let me see. So if we go to this first return here, CEA, and I go to the first load of that function, then we see here, so it's written these things in C000, right? So these are 8 bytes, and each byte has one row. So the pixels, the patterns are 8 by 8. So we have 1 byte representing 8 bits, 1 pixel per bit, and we have 8 rows, right? So we have 64 things here. So if we put like 0f, that would mean that the first 4 are unset and the next 4 are set, right? So it's in that way that the pixels are defined. Okay, I'm mixing OF and F0, but that doesn't really matter. So now if we go look to that table, that's what I typed in. So I mixed OF and F0, right? So they're switching about a bit. But that's how the characters are made up, and that's what I'm trying to extract from the thing. And then it just boils down to mapping the information. Okay, you can see my pattern here. So the composition, all these tiles reference to the pattern table by ID, and I'm just, I have to make the link, right? So pattern 15 is then like, consists of those pixels and those colors, and that way I can extract the exact information that I need from the game. But yeah, it's quite complex. So the first thing went quite smooth, right? The extraction of the compositions of the tiles. What we're doing now is the exact pattern data here, the pixels of the patterns. That's quite a bit more complex, but no big deal. We'll figure it out. So yeah, we started here. So we have a rep count of 7 and a rep count of 1. That's what I want to verify. Let's close this. So we have to break, let's see, so not the return, but I want to know in the loop whether my repetition counts at least are correct, right? So a 7 for the first and a 1 for the second. And the loop that writes our data is here, right? So CD6, so here we load the byte and here we load the counter. Okay, so at this point we're loading the repetition count into our B register, which is used by DJ and Z as the loop counter, right? So DJ and Z decrements the B register every time it loops. Yeah, well, I know I can just copy these things from the emulator, of course, right? But the point is to load the load the ROM and just extracting it straight from the bytes themselves, right? Because that gives you the possibility to override that data with different data as well. So if you want to replace the sprites, make them look different, that's how you would do it. Because you would do the encoding algorithm like inversely, like in the other way. And then you can write actually data into the ROM and have new sprites and stuff. So yeah, that's what the goal is. Okay, so we are here. I'm going to load I'm going to break on the start of the function 2 though. So we can see that we have the correct pointer here to 8B97. Okay, that's not the correct one. Wait, why is it? Oh, right, I'm in the process of okay, that's not good. I need to, that's B506, that's incorrect. I need 8B97 in HL. Okay, and it's going to start when the demo starts. Oh, I have many copies of the ROM, that's not a big deal. So I did make a thing here already where you can replace the the level data. So what I did before is I extracted all the levels, right? So I figured out how the level data worked, and I've extracted these all straight from the ROM, right? And then, oh yeah. Well, no. I'm modifying the ROM file on disk, right? And then you have a different ROM, and you just load that. So you're making a different ROM file. So I've made this construction mode where you can make your own levels, right? You can change the levels however you want. And this exports to a puzzle file, but I've also made it so where you can download an entire ROM pack, which contains like 105 or 115 levels, which you can just download. And this, so you have to provide the ROM yourself, and this thing will override the actual ROM data, which you then download, and you can just load into the game. And then you can play these rounds, these levels yourself, as if it was like that in the original game. Like you just make a copy of the file, right? Okay, so 8B97, here we are. This is the correct one, so I'm going to reactivate my breakpoint here. And the first one should be a repetition count of 7, which we should see in our B register here. And of course it's A0, so that's already wrong. Oh, no, we haven't done it yet. So, okay, so A is being copied into B, but A is 8, not 7. Did I forget this increment? Where's my code? Oh, yeah, of course. Why am I outputting this here? I should output this here, of course, after the last... Yeah, the first, of course, the first rep count is 8. And then we do a 1. So the 8 is at least correct, right? Yeah, so the game does come with a construction mode, right? So back in the 80s, when I was playing this game as a kid, we could replace the first 5 rounds. That's like a feature of the game. And then, but only the first 5 rounds. And you could export those 5 rounds to disk or cassette tape. You would write it, and then you could exchange that with your friends. So people, there is like a community, or there used to be a community of people that would exchange custom-made levels. But the thing that I made was, first of all, I made it so you could do it online with an online editor. And also the fact that you can replace more than the 5 rounds that are in the first 5 rounds in the game. So I can replace all 105 or 115 if you include the bonus rounds. Yeah, that's because I just figured out what the algorithm was for storing the level data in ROM, and then if you reverse engineer that algorithm, you can just reverse the reverse and then just write out new data, right? And it just happened to be a very simple run length encoding algorithm, which was pretty cool for 1985, of course. But yeah, so I'm capable of writing completely new levels, more than 100 in the game, whereas previously you could only do like 5. Okay, so 8 is correct for the first one. Then the second iteration should be 1. This might be wrong already. B is 4. Yeah, it's going to be 4. That's already incorrect. Yeah, exactly right. So once you know how they did the original compression of the data, because they had to compress it, right? They have like a size limitation here. So once you figure out how they did that, then you can just run your own data through that algorithm and just replace the stuff. Yeah. Okay, so my second iteration is 1, and in the game it's 4. So I guess we do have to run through the entire algorithm to see what I'm doing wrong here. Can I deduce this from the data though? So A7 are 7 repetitions plus 1. So wait, what's our bit pattern here? Okay, so prefix 1 is ANDed, right? So if you look at F8 bitwise, then F8 is of course 1 1 1 1 and then 1 0 0 0, right? So we're separating the bottom 3 bits from the top 5 bits, right? That's what we're doing, right? So the top 3 bits from the bottom, the top 5 from the bottom 3 bits are separated, which happens in this AND, no, not that AND, this AND. Well, actually we're inverting, but sure. So if we're inverting, that means we're taking the bottom 3 bits out, and that makes sense. And that would be the repetition count. Yeah, I think it would be. Uncover bits by seeing if the file size changed by flipping. Yeah, that, exactly, right? That's what you do, right? I did make a video about this, where you just change one little thing and see what the end result is, right? I think I have, because I made a blog post about that as well. So if we go look in the thing here, so this is the blog post that describes how the level data was stored, right? Well, maybe I didn't make an example of that exactly. So what I do go on about is this is the construction mode, and then we save the file to compare it how it looks on disk, right? And then I noticed that the level data is like exactly the same on the file itself as it is in memory, except for like a file header. And then you make like, this is not a minimal change, but you try to make a minimal example, and then you see how the file changes. And then you pinpoint exactly where the level data of the first round is, because an exported file contains 5 rounds. This is 5 rounds in this entire piece of data. But if you compare the two, all this stays the same pretty much, and only these bytes change. So that's how you figure out like, like that's indeed a thing that's definitely a known thing. Yeah. I mean, it was fun though. Like it wasn't that hard. Like I said, it was just a simple run length encoding, because they wouldn't have used much more complex things in back in the 80s, I guess, right, with limited compute performance. Right, so we're extracting the bottom. So the bottom 3 bits contain the repetition count. In A7, that would be 7, right? Because A7, the bottom 3 bits of A7 are, of course, 7, bit 1, 2, and 4. And then what do we actually write? We're testing the bit, we're comparing, that doesn't matter. We're increasing A, which is still the repetition count. Oh, and we're loading the byte itself again. Or the next byte, because we incremented. Okay, so it is a combination of these two. Sure. So we're writing 7 times 0, and then, okay, and then we have 0 as the result. And I do indeed. So A0, the bottom 3 bits of A0 are 0, right? That makes sense. That would be changed to 1, because we're adding 1 regardless. That's this one. Increment A, which is the counter for the loop. But the game makes 4 out of that for some reason. So we have to trace where it gets the 4 from. Unless I'm doing, oh wait, C is prefix 1, right? Which is F8, which also this is in play, right? Oh, it isn't. Okay, I have to loop through the loop through the code here. So we have to reset and start at the start. Okay, I'm going to disable for a moment so we can go back to the main menu and wait for the demo to play. And the target pointer is 8B97. Yeah, that's the first one. Okay, so we start with this. This is fine. So we're loading prefix 1, we're loading prefix 2, pushing it on the stack, that's fine. Then we're loading the current value, which is the third byte now, which is A7, all right? So that's A7 in the accumulator. We're ANDing it with prefix 1. Prefix 1 is F8. So, wait, I'm gonna get my... Okay, so there's top 5 bits. Oh, wait. So yeah, F8 is of course the top 5 bits are set, and we're ANDing it immediately. Oh, so we're extracting the top 5 bits. Wait, does that make sense? So ANDing it with C, so A7 and... Wait, am I mistaken now? I don't know, we're starting at 8B97, right? Yeah. Why are we ANDing with... Oh, no, we're ANDing with F8, of course, yeah. I was looking at the B register, but we're ANDing with C, which is F8. So we're extracting the top 5 bits then. Yeah, we're not inverting yet here. Okay, we're extracting the top 5 bits out of A7. Which is A0. That makes sense, right? We're dropping the bottom 3 bits that would make it A and 0. Yeah. Okay, so my first interpretation was wrong then. Okay, sure, that's A0. Okay, we're comparing that with the other one, which is A0 as well. Like I do realize that the bottom 3 bits are the repetition count, and I'm not sure exactly what the top 5 bits represent. And I mean, they're going to be settings, right? Like conditions, flags, or whatever. Because based on that, we're doing we're taking specific jumps. Right, so if we have A0 and we're comparing it with the second prefix, which is also A0, right? So that should be 0. And so we're not taking the jump, right? So A0 minus A0 is 0, so the 0 flag is set. So we're not taking this jump. So it is not a 1 repetition count, because 6CDE is our 1 handler, right? We're loading 1 into B and we're writing out the byte. Right, yeah. Then we're loading prefix. So now we're inverting the prefix 1, which is F8 becomes the inverse, which is, of course, the bottom 3 is 7, right? That's the bottom 3 bits set. Right, so we're loading F8 and then inverting, which is 7. That makes sense, right? And we're ANDing that. So we're extracting the bottom 3 bits from 8B99, which is still the same thing, right? Yeah, and that's our repetition count. So that makes sense, okay? And then we're progressing to the next byte. So that the next byte is now the 00. That will be our byte that we write out into memory. Yeah. Okay. we're testing bit 0 of prefix 1, but that's not set. So wait, is it a... We're testing... That's F8. Yeah, that's F8. The bit 0 is unset. Oh, it is 0. Yeah, okay. That's why we're taking the jump. So we're not rotating. That's fine. And now, so we're doing 7 minus 2 is 5. The carry flag won't be set. We're not crossing the boundary here, right? So the carry flag, I'm going to get the flags here. Right, the carry flag, oops, is at the moment 0, and it won't be set by this comparison. Right, so we're not taking the jump. Okay, makes sense. We're increasing A. A contains the repetition count becomes 8, right? And now we're writing out. So we're doing 8 writes. So I'm going to jump here, so I don't have to wait for the 8 writes. So if you look at C0, C000, this is going to become 8 zeros, right? So these are now 8 zeros. And now onto the next byte. So we're still pointing in memory to 8P9A, yes, which we're incrementing now. So now we're pointing to the next thing, right? A0. Okay. And we're jumping back up. Okay, next iteration. So this is where we make the mistake, right? Because I'm counting this as 1 and the game as 4, and that's not correct. Okay, we're pushing BC. We're loading A0 into A, and we're ending with the prefix 1. That would make it A0 still. That doesn't change. We're subtracting prefix 2. That becomes 0 because they're both A0, right? So this doesn't, it's not a 1 repetition, okay? We're loading prefix 1 into A and inverting, so now we're extracting the bottom 3 bits, which is going to be 0, because we're dealing with A0. The bottom 3 bits of A0 are 0, right? We're inverting and ANDing. Yeah, AF, like the A register is 0 now. And we're going to the next byte, which is the value that we write, which is also 0. We're checking the bits. That's always going to be false, because it always refers to the first prefix here, A0. So that's never going to change. So we can ignore this rotation all the time. All right. Okay. So now we are carrying now, right? Because we're subtracting 2 from 0. So the carry flag will be set now. Right? Yeah. Okay. Yeah, so now we're jumping to 6CE2, which is this one. Wait, wait, let me look at my code again. Yeah. Okay, so it is this one then. Okay. For some reason I don't trigger this. So why is my repetition count not 0 at this point? Oh, no. Yeah, wait. No, it's this one, right? Where am I looking here? Where's my PC? Wait. Oh, PC is here. Yeah, it's this subtraction, right? So this should trigger though. Why is this not 0 minus 2 smaller than 0? That doesn't make sense. Okay, why are we doing this twice here? Because, yeah, this is what we're seeing. Why is this repetition count 1 here, though? Oh, did I just... Okay, I stupidly outputted it twice. Oh, no, it's this one. Oh, wait, we're triggering this one. Right. Yeah. Why are we doing this here? This is not correct. Yeah, we're doing... But... Oh, am I... Oh, right. I'm not... I have to increment twice. I think I'm processing this byte, the 4th byte, as a value that's being... that contains a repetition count, and that's not correct. Yeah. So... This needs to be +2. Yeah. And actually, I'm going to put that at the end. Yeah, current value is being saved. Wait, why am I not setting current value in this thing here? Actually, current value is A, though. I think I should just leave it at that and not use current value. Or in fact, yeah, I'm not assigning current value either. I should do that too. Wait, let me think. Wait, we need to increment twice though, because otherwise we are using this byte as the repetition count. Oh, that doesn't make sense. Oh, wait. So let me ignore this. I use A because we're initializing A before we start a loop. And we're going to write out A instead of current value. I'm mixing two. I'm putting two variables with the same information. That's not good. This is not going to change anything though. Yeah. So our rep count is 8. That's good. Let me write out what we are writing out. A supposed to be here. Repetition count. Yeah, so the data is incorrect. Why is the data incorrect? So A starts at 2, that's correct. We are immediately in this situation. That should be Oh, I have to assign the, okay, sure. I have to reassign A at this point in time as well. Yeah. I have to do that because of the skipping of the byte, right? Yeah. So we're writing 0 for 8 times. Then we come in A0, and then this one triggers. Does it? No, it doesn't. Okay, now we have a repetition count of 0. Okay, and we do exit. And this exit means that we are triggering our thing here. Now I wrote that this is an exit condition, but I think it is. It can jump to a different function though, a different part of the function. So let's look again here. So if this subtraction, this comparison with 2, like the -2, this is 6CE2. Yeah, so we're testing something. We're testing something else, and then that's the exit condition, but these two can make it jump elsewhere. Right, so let's try to get these two conditions in the code. So we're testing A for 0. If it's not 0, then we're jumping. Okay, A meaning what at this point? What is in A? 6E2. So we're jumping from here. We're comparing that the repetition. Okay, so if the repetition count is not 0, right? Because we're subtracting 2 from the repetition count, so that's what is in A. Yeah, and we're testing it for 0, but I think we have 0 though. Yeah, how is our repetition count not 0? Because we're using the value A0 as our data, right? And how we extract A0 or the repetition count is ANDing with the inverse of the prefix. The prefix is still F8. The inverse would be the bottom 3 bits for A0. That is 0 though. So how does that not? That doesn't make sense. So where are we? Yeah. So we're jumping to 6CE2. A is 0 indeed, right? That makes sense, right? The bottom 3 bits of A0 are 0. So let's take this jump and see. Right, so we're testing A for being 0, right? And if it's non-zero, we jump out of this. Oh, but there's a different check. So this one will fail then. Okay. Yeah, this one fails. Okay. So if let's see, what is the logic here? If A equals 0 or something else, then we return. Okay. So this check is if repetition count equals 0 and something else, then we break. Or that's an or, is it an and? No, it's an and, right? Because we're doing something sequentially. And then what is the next check? So we are checking the repetition count for being 0, and then we're loading the byte into B, incrementing and checking whether that's 0. So HL is at this point pointing to 8B9C, which is the value. Okay, as the one beyond there. Okay, we're incrementing it by 1 and checking whether that's 0. Okay. And the targets are the same, right? The target for the jumps, yeah, 6 CEB. Okay, sure. So data current data index plus 1. Do we use A here? No, not yet. So I think we're already, yeah. So that's just A, right? And then the check is A plus 1 equals 0. How is that possible though? Unless that's FF or whatever. This is still wrong though. So we're loading HL into B, which is then 0, incrementing it by 1. So does the increment have an effect on the 0 flag? I don't know that by heart. So increment B, was it right? Yeah. Okay, adds 1 to B. C is unaffected. Z is as defined. I mean, they could have put a slightly bit more information than as defined. I mean, we can check that though. So we're loading a 0 into B. Yes. Incrementing, that becomes 1. I mean, the 0 flag is not set, so I guess an increment. I mean, I can force the value though. I should force the value. So I guess if that is FF, then that becomes 0, and then we are also escaping the function. Okay, that could be like a stop thing or whatever. Yeah. Okay, so we are making the jump here. Yeah, so A has to be unsigned as well. Signed as well, because we need to go negative here. And now we are here, do extra stuff. We should end up here. Why do we get output? Oh, yeah, because I don't break anymore. Okay, sure. Right, okay, but that's a whole bunch of nonsense, I guess. Yeah, so this is what I was looking for, right? So we are doing extra stuff here, which we don't know, but let's look at the output to see if it is indeed somewhat correct. It's not gonna be though, but okay, we got quite a bit here. Yeah, no, so it fails. So the first 8 are correct, but then it starts to fail. Yeah, that's not correct, I think. I think it should be 2 sets of 8 zeros. Yeah. Okay, so the fact that I'm not breaking here does indeed mess with the things. So now the problem is that we do have to implement 6 CEB though, which is this one. Oh, and we're doing L there. So we're batch copying, I guess. Okay, we can't really help that, of sure, but yeah. And the question is, do we ever return to our initial routines here, though? So is there a jump back? Where was the jump to 6 CC0? Is that correct? Yeah, that should be the entry point for the big loop, right? So do we have other jumps to 6 CC0? No, we do not. So we never return to this part of the function though. Because now we go, so if we look at all the jumps, right, starting from our starting point here, 6 CEB, that's the new section. If we look at jumps, 6 DO5, that's right here. 6 CDA, which is, oh, okay, so we do jump back here. Okay, that's just after our writing loop. So we do return all the way to the top because we're incrementing HL and then we're jumping back to the top. Okay, so we do return there. Okay, because this part is our main while loop, right? So we have to take care. Like it could get very complex if we have to do like another while loop for something else, right? But no, it does return at some point. Of course, I name it the same in both functions. Okay, so we don't need this one anymore. I mean, I should name a current value, but that's fine, I guess. Okay. So yeah, this is the extra stuff we're looking at now, right? So 6, what was it? 6 CEC, 6 CEB. What does the accumulator contain now? That's the repetition count, right? We're coming from, these are our 2 test conditions, and we're testing for 0, so that doesn't affect the accumulator. That's the repetition count, right? Because we're checking the, so that's our current accumulator, right? Also, should this be at this position? Oh, that makes it complex though, because we're doing stuff here now, but it might influence, like this might influence things, because this belongs to like the upper part, right? I mean, we'll see if we encounter it though, because that happens. That's this increment here, right? I think. Okay, we're loading the repetition count in B, so we're saving that temporarily, and then we're loading the current byte into A, which would be that 0, right? Which makes sense because we do have to write out the 0 8 times again. So everything between these 2 exchanges, we have to make sure that we don't confuse. So DE contains our current position within our output thing here, right? So we're currently looking at this position here. We're going to exchange that. So these additions, these doublings are on the output, not on the input, which would be HL. Okay, so we're loading A into L, okay, and 0 into H. So the top part of the 16-bit value becomes 0, and the bottom part, okay, sure, because we're doubling. So we're doubling the repetition count 3 times, and then adding it to this position. No, because DE is exchanged, so that contains. Wait, let me check in the code here, right, where we end up. So we're taking the jump. We're pushing HL, sure. Loading A into B, we're just saving our current value. Now we're exchanging DE and HL. Well, I mean, we're loading HL into A, which is also 0, right? So we've saved our repetition count and our current byte that we're doing. We're exchanging DE and HL now. So these are going to get flipped. Wait, no, that's not what happened. Okay, I have to look up EXX again. Oh, no, we split the primes. Okay, sure. Right, these primes are getting switched. And the only, yeah, I think we're saving our pointer to where we are here. Yeah. Because what we did before, we did do an exchange here too at the start of the function, right? And that was only applicable to DE. So I think we're saving, yeah, we're storing C000 in DE prime here. Yeah. So I think it's just keeping a reference to where we currently are and the start of the thing. Okay. So we're loading A into L, so HL becomes 00 and then 00 for the repetition, right? Yeah, HL is 0. We're doubling that 3 times, but that remains 0, and we're adding DE. Okay, that's the base pointer of the output array. Becomes C00, of course. So we're doing positional stuff though. And we're pushing HL on the stack. Okay, and then we're swapping the primes back to where we are just to get our DE thing again, right? We're restoring the state. Okay. And on the stack, we do now have C000, which we calculated, which we're popping back off the stack. Okay. Why would we be doing this though? Loading B into A, which is our repetition count, I think it was, or the value, one of the two. Testing it for 0. It is 0. And now we're doing a mask copy. Okay, and now we see so the LDIR is copying 8 bytes, right? We're loading BC with 8. So we're going to block copy 8 bytes from the start, from C00 to the next C000. One moment. Yeah, so we're doing a block copy of the first 8 bytes, so it knows that the first 8 bytes are the same as the next 8 bytes, and it's doing a specific routine to duplicate these first 8 into the next 8. And like, this is sprite data, right? So apparently it knows, it has an instruction to just copy the previous a set of previous data into the current data. I mean, this makes things quite complex, but sure. Right, because like if we execute this, we're going to copy the first 8 bytes. I mean, and they don't necessarily have to be zeros. Yeah, it's just a copy of the first 8 bytes. Okay, so this does a block copy. How can we do that? The question was, did we start from 0 or did we calculate 0? Oh, that is exactly this, right? So we're starting at okay, that's the offset then. Wait, no, because we're doubling this 3 times. So the problem is that we're doubling this 3 times. This makes it hard because we had 0 as our initial value. So doubling that 3 times and then adding this DE doesn't really do anything because it's all 0. So, but this calculated C000, right? Based on what the accumulator and DE was at the time. So DE was just the start of the output area, so we can ignore that because the C000 doesn't mean anything in our C++ code, of course. That's just the start of the output data, right? So if we're looking at offsets, we can just start from 0. That doesn't matter. So the bottom 8 bytes, like the bottom 8 bits of the HL register becomes A here, and that was either value or repetition count, which I can't remember. Well, I mean, it's this one, right? It's the byte. Literally, yeah, it's literally the byte, the value. So that would be this 00, right? Which is now not a value, but an offset then. Yeah. And it's a hard-coded 8 as well, right? So I think this is just an offset from which we copy 8 bytes into the next 8 bytes, or into the current position, because we calculated the current position. I don't know. That's just where we are left, right? That's, we keep a running tally of our position into the output buffer. Yeah, so we do know where we are. And this thing contains the position within from the start that we have to copy. Although we do, so why do we multiply this 3 times or double this 3 times? Like it's always going to be like a multiple of 8, right? Because what they're doing is they want to like duplicate entire patterns, right? So 8 bytes here is one pattern, and this code clearly copies 8 bytes. So they're trying to say copy this source 8 bytes to the next we are handling here. It's like a duplication thing. So let's say, well, I don't know what the value is going to be. Oh, is it an index? Is it, so if this is 1, right? So then HL is 1 at the start, becomes 2, 4, 8. Yeah, and that is exactly right. It's an index. So let's say we want to duplicate this set of 8 bytes. If we look at this, as if they were patterns, then this is pattern 1, right? And this is pattern 0 here. So this has index 1. If we need to calculate the offset of this first byte, in other words, our source byte that we're going to copy, relative to the start of the array, then we have to, and we store this as 1, meaning 1 is the first pattern, pattern 1, as in the second pattern. In order to find C008, the address of this thing relative to the start of the array, we have to multiply 1 3 times. 1 becomes 2, becomes 4, becomes 8. Right. And 8 is, of course, the thing we add to C000, to the start of our thing. So 1, 2, 3, 4. If it was 4, then 4 becomes 8, 16, 32. Does that make sense? 8, 16. So we have C018 here, right? So 18 hex is 24, of course. So if we do 4 times, oh no, it's 4 plus 4, oh, it's plus, right, wait. Yeah, we're doubling, times 2 times 2 times 2 is 32 now. Oh, wait. it's 0 based. So 4 is, this is not 4, this is 3. So 0, so 0, 1, 2, 3, 4 is indeed 32 bytes added to C00, because that's C020, which is indeed 32 more. Yeah, it's 0 based, obviously, of course. Yeah, that's it's an indexing thing. That makes sense, right? And then, so after we do this, we exchange back, we pop HL again, so we're back on track here. We're loading B into A, that's fine, ending A. Wait, do we not return immediately because we're doing another L there? Oh, no, that's the actual copy, sure. Yeah, we have our offset, we have our L there, we're popping HL again. Yeah, this is our popping of our HL. And then we're doing an unconditional jump to 6 CDA, where we write out, oh, we're incrementing HL, so we're going to the next byte, sure. Popping BC and jumping to 6 CC0. Wait, but we haven't written out the thing though. Oh, no, because we block copied. Yeah. And we're doing the next byte. Okay. So nothing strange is going on here. This is just a block copy of the thing, and the condition to whether it's a block copy of or not is apparently this. So if it's a negative repetition count, or repetition count -2 is negative, then we check whether it's 0, because that would mess with, yeah, we can't. So a repetition count of 0 means that becomes the index that we have to duplicate, right? It wouldn't make sense if it's 0, is it? I'm not sure exactly what the conditions are to skip this block count, because we just exit the function. That means things are done, right? This break implies that we exit the while loop, and we're done with writing the thing. So that's not super important. So we're going to have to use a continue after this here for sure, because we don't want to be doing this. We're going to, what we do need to do is we need to increment our current data index, although we already did it +2 here, so we have to maybe adjust here. Yeah, I'm not sure, but we have to make sure that the current data index is correct here. So what contains? Oh yeah, it was the value, right? The value contains the index of the sprite we have, or the pattern we have to duplicate. Which is not repetition count, but A in this count. I think I'm gonna rename A to current value though. Okay, stupid. I hate when it does that, like just within this function. This is a variable local to this function. Why would you suggest editing that in a different function above here, even though it's the same? Is it still compiling now? Nope, I'm missing one probably. Yeah, AM prefix, that's here. Where is it? Here. Still not. 126 and 139. Okay, another one. 142, of course. Okay, now that we continue, we're having a seg fault here, but that's fine. Oh, are we always triggering this? Why would we? why would we crash now? Rep count 1 is it's always going into this one here. This is because I changed it to a signed thing. No. Why are we always triggering? Oh, no. Okay, it's looping. Okay, sure. We're never breaking. That's why we're because the thing loops here, overflows here. Okay, let's. Yeah, because we're not progressing the bytes, so we're never going to hit this break condition anymore. So I'm gonna temporarily make this a break condition. Just so we see that we don't crash, right? So yeah, this is still correct. I'm gonna remove these extra things here. Also, this can go outside of this. And this should be current value. We shouldn't re-index this here. And this can go outside. And this is a forced rep count of 1. And then okay, we'll leave this out, and then this, and then we're writing out this n times. Yeah, so yeah, we have to write out and then continue, but we'll do that later. Okay, it's being stupid now because it's a signed value. Okay, so the do extra stuff is still in there. Yes. So now we have to do a block copy. Let's see where we how we can do that. So repetition count is the current value, is the pattern index is this. Yeah, that's correct, because we are indeed duplicating the first 8 bytes. Then we need to calculate the offset within our output array, which is the multiplication or the doubling of the thing 3 times. So offset equals current value times 2 times 2 times 2, right? That's what the thing indeed does. So we'll keep that the same. Yeah, that of course is 0. So it's stupid that it's 0 now, because that messes with our calculations, as in we can't verify if it's correct, but I'm sure it is. And now we just have to do that, right? With a simple for loop. I'm not gonna be very efficient here. It's 8. Yeah, that's hard coded. And then we will write, no, not data, output. current output index, and then we'll increment current output index by 8. And this needs to be added with I. We will assign output not current output index, but offset plus I. Right, that's the block copy, right? Yes, now we have a length of 16, so we duplicated the first 8 bytes to the next 8 bytes. Now the problem is, like, this break needs to be a continue, but now it fails because it loops forever and it crashes. So I can't see the top here. So there is something wrong here. So let's see what we can do with the first thing. Okay, so this is the start of it. So we're writing 0 for 8 times. Then we're doing a block copy pattern of index 0. Oh, and then we fall into the rep count 1 loop, I think. Yeah. Okay, now it's messing up. Also, this needs to be cast. Right, so why do we end up with an infinite loop here? So after this continue, which is correct, right? Because we just skip to the next thing, we end up in this clause, and then we are writing, we are writing it out and going to the next. So the bytes are progressing though. We can see that they are progressing, but I might be off by 1 where it interprets the order of the bytes incorrectly though. So that might be the case. Let's see. We're still here in the code after the block copy, so we can see what it does next, right? So we did a 0 and 0, 0. So we should be pointing at 1C now, which we will process. Yeah, because 1C, current value is 0. That should be 1C, so we're definitely off there. Yeah, I think I will fix that immediately because that can't be correct. So we calculated the repetition count and the current value for A0 and 0, 0, right? So how does current data index not point to 1C now? I mean, what I'm saying is, why is this not enough? That should be enough though. Oh, we're not assigning. That's why. Like, we're continuing here, so we're not executing this last line. I think that should be it. No. Well, at least, yeah, at least we're handling 1C. Yeah. Okay. So at least we're on the correct byte here. That's better. So let's see where we end up now, right? So we're popping HL after the block copy, which is 8B9C, which is still the value byte. We're doing an unconditional jump to 6CDA. Okay, and we're increasing. So now we're already pointing to 1C, or also pointing to 1C now. Yeah, 8B9D, that's good. And now we're back at the start, right? We're popping BC. That's our 2 prefixes, A0 and F8. And we're doing an unconditional jump to 6CC0, which is at the top of the thing. Yeah, so we're fresh on top of the loop now, of the top of the while loop. Right, so we're loading 1C, okay, ending it with prefix 1, which is F8, meaning the top 5 bits. Yeah. So let's see what that looks like. One C. One C, only the top 5 bits. Okay, we're losing this bit. That becomes 1/8 or 18 hex. It should, at least. Yes. And we're comparing that with our other prefix. And we're jumping to 6CDE. Oh, that's the 1 repetition. Okay, so fine. That's correct then, because that's what we were doing here too, right? 1C is 4th rep count of 1. And then we're writing 1C 1 times. Okay. Okay, so that appears to be correct. Okay, we're loading 1. We're jumping to the write out routine. We're loading HL, which is the byte 1C again. We're loading that into C000. Okay, increasing DE. So that should have our 1C. Yes, it does. And we're not looping because it's only 1 iteration. Increasing HL. Now we're pointing to 3C. And we're popping BC again. So we're starting at the top again, right? So now we're doing the same thing. We're starting again at the top, loading 3C. Again, getting the top 5 bits of 3C. Again, that becomes 3/8. So I'm assuming that is just correct then. That's also because the bottom 3 bits are 0. Actually, to determine whether we are doing a 1 repetition, we AND it with prefix 1 and subtracting prefix 2, right? So prefix 2 is in our case A0. Which is 160. That value doesn't make sense. Only in the context of this condition does it make sense though. And how does A0 look? Well, that's just 1010 and 4 zeros. Wait. Yeah, that doesn't really make sense to me what that value actually represents, but fine. Sure, so that becomes 3/8. Yeah, it's the subtraction of the top 5 bits minus the other prefix that determines whether we do a 1 repetition or not. That isn't exactly clear to me why that would be the and they made it dynamic, right? Because these 2 prefixes are within the data itself, so they can alter this around to adjust for other, like to adjust these values, these cutoff points for other arrays of data for some reason. So yeah, we're subtracting 160, was it A0? Yeah, so we're subtracting 160 decimal from the top 5 bits of the value. And if that is less than 0, then, or bigger, I guess, then we make it a 1. Yeah, so this is also 1, yeah. I mean, it makes sense though, because these values, this 1C, 3C, that has to be copied over like verbatim, but weird. So I mean, fine, sure. This one is correct as well then. Because I'm doing the same thing, right? Force rep count, wrote it out 1 times. Then we go to A3. So these are all going to be the same, I think. A3, 1C, 3E. Then we have a 0, though. That's going to be interesting again. Probably 3E and 0 are again one of those either block copies or multi-byte copies. So let's see. Okay, so we're writing out, we're not looping, popping, jumping up top. We're loading the next byte, which is A3, ANDing it with the prefix becomes A0. Oh wait, A0. Now we have a matching thing. The 0 flag is going to be set. So we're not jumping to the 1. Okay, so now we're not supposed to, yeah, for 4 times. Yeah, no, I did have that correct though. So we're writing A3 4 times. And 3, it's 3 plus 1, right? Yeah. Yeah. And we are writing the value 1C apparently. So we're calculating based on A3. So is that the top 5 bits? No, that's A0. Oh, no, it's the next byte. Yeah, A3, that when it's a multi repetition thing, it's 3 times 1C, which is the next byte. Okay. Yeah, I mean, this is correct though. I don't know if it crashes still. Does it still crash? I'm gonna remove the less here. No, it doesn't crash, and it is 2048 bytes long, which is exactly what I was expecting, so this might just be correct. We might have completely re-implemented the thing here. I still didn't fix my first byte with my modulo operator here, but fine, I guess. I mean, that sucks though. Why does this not work? This is so simple. This is so stupid. Wait, is it 15? It's 15, right? No, well. No, because now... No. Oh, should that be not equals 0? I mean, that's embarrassing, but... always something like it's doing the same thing. Yeah, that's what I'm trying to prevent, right? The 0 also as the modulo trigger. So oh, is it because we have to do, is it as simple as that? No, it's not. Yeah, you have to do 1 based, I guess. Yeah, we do. Okay, that's fixed. Yeah, because now it has to match up, right? Actually, if I'm going to add double spaces here. So we can separate them a bit. Okay, let's look at the output. Let's stop at the return. I can't remember which return it was that that triggered the exit. I think it was this one. Let's see. No, that's not a return. It's either this one. Yeah, it might have been this one. Yes, so I think now we are complete. Yeah. No. Listen, this stacking of things, no thanks. Okay, let's compare these. Okay, we have 1C3C, 1C3E, 3E6707, 1C, 37E7F. Yep, that all looks quite similar. Yeah, that looks pretty much the same. Okay. I think we have decoded the sprite, or the patterns, at least the pattern table. So let's now convert one sprite into pixels. Yeah, let's do that, so we can see visually that we have extracted the pixels at least. Now let's see at the end too. So that would be C00, the C800, right, is the end. Yeah, we have a couple of zeros. Oh no, that's incorrect. Yeah, that's incorrect. Because we have C zeros and then 80, that's here. But then we have 03, 03, 03 instead of C0. So there is still a bug here though. Yeah. However, I am going to visualize first, so we can, because that would be way more, like we would see that way more easily if we actually visualize the pixels, right? So how are we going to do that? Let's make a different function for that. Print pattern. Now, what do we need? I guess we can just get a pointer to a uint 8t, right? So I think we can assume that we won't overflow. Oh, and we need an index. Actually, where did we save this? Actually, this is returned, right? Is it returned? No. Oh, it's outputted. Okay. Yeah, we need to return this, I guess. But that's a buffer. Yeah, that's our std array, of course. I mean, we'll have to output it inside this function then, which is fine. Yeah. Okay, so let's pass this as a... Was it 1496? I can't access the... I mean, I could, but I'll have to reorganize this a little bit later. That's fine. And then so we have to loop this 8 times, starting at pattern index times 8. Yeah, then we access the 8 bytes, and then for each byte individually we check the bits. This is, of course, uint 8t. we're starting at pattern index times 8. And we only have to do 8. Well, no, let's just do from 0 to 8, right? That's easier, I guess. And then we just calculate a value. Then or current equals data at index, or can I do at pattern index times 8 plus I. That's our thing, right? That's our indexing. Yeah. That's no, wait. I don't know. We're looping every byte at that location. Okay, and then now we have to check the bits, which is another loop. But can we do? Yeah. Can we do this with a loop? I mean, we have to, right? Now we have to check whether I mean, it's 1 to 4. It's 2 to the power, right? I mean, it's 2 to the j, right? Does this work? No, that's XOR, right? Can we shift that? Can we work with bit set or something? We do have a subscript operator in a standard bit set. That's good, but then we don't have to think. Okay, that's spam. Right, so we can index here, right? B3 is just a standard bit set of 8. Can we cast from a byte? Yeah, we can. Let's see, I haven't used a bit set yet. And then we can do current I. Of course, that's J, not I. Let's output a thing. Let's see if we can get yeah, no, let's get a Unicode block or something. Okay, nothing copy pastable. Usually they have like copy pastable stuff. Full block. I mean, I guess we can do that a bit more compact. And then we add a new line. I don't know if this still compiles. It apparently does. And then for each current output, okay, so now we know we have 2048, so that's divided by 8, right? Actually, I'm going to not do a skip. I have to move that function above here. Pattern index I. Because I don't have function declarations at the top, but that's fine. Okay, that doesn't work at all. Why is it doing? Oh, is it? Why is it not printing my block? Okay, now it is. Okay, good. I mean, we see certain things, but they're not. They don't seem to be correct though. And we have 256 patterns. Yes, but they are not. Oh, they are. I think I have to invert them. Maybe. Let's invert them. Although yeah, this is the alphabet though. Yeah. But they're mirrored. Okay, sure, they're mirrored. That's why. Yeah. So we start at 7, I guess, and larger than 8, and then. Oh no, it's not. I don't have to flip that, right? I have to flip the bytes here. No, that's up and down. No, I do have to flip. Why? Why does this loop 7 larger than 0? Well, okay, let's go and then go -1. That doesn't really matter. Yeah, there's the flower, a heart. Here's the alphabet. Yeah. We have correctly decoded these. And I'm going to invert again because I don't think there's a reason to. Oh, right, these are the borders. It's loading the main menu now. Yeah. So these are the pattern tables for the main menu, and those contain the borders for the thing, right? That's why we don't see Lolo here, I think. Yeah, I'm gonna invert again because there was no reason to, I think. Yeah, we have this is goal facing to the right, which is on the main screen. That's why he's there. Yeah, we have our letters here, our numbers. That's an arrow sprite. And then indeed it starts with two empty ones and then the 1, 2. Okay, let's let the game load and let's compare. I mean, it is correct though. We can already see that it's pretty much correct. Although we did see some different numbers though. So see if we can spot the difference there. Oh no, this should be the game though. Oh, but remember it loaded it 2 times, so maybe there's a bug in there somewhere where it loads it twice. So let's look at the tile viewer. So yeah, we're starting with, I don't know why this one is green now though. But that's not that important. So yeah, we have 256 patterns. The last one is the king. So this is a different thing. I have to go back to the menu. Yeah, let's pause here and let's look at the thing now. Yeah, this is what we saw. Although the last one is also so this is the one that's wrong then. Because if we look at our patterns here, we start with 2 empty ones, right? We have 2 empty ones. No, we don't. One should, okay, it immediately starts with a 1, 2. And the 1, 2 was in game, right? You have to wait for the demo again. Yeah, so we have 2 empty ones and then 1, 2. And then we have the ladders. Yeah, that's correct. Then we have the exit thing. And then the open exit, yes. Okay. Then the arrows. Then empty one and an asterisk. So there's in two colors, but we don't have color data yet, right? And then this little T, I don't know what that is for. What is that for? I'm not sure about this one, but we do have it here too. And then we have the respawn thing, border thing, I think, and then the hearts. Yeah, so where are we going wrong here though? So those are the hearts, then they have the numbers with the dots, and then a T, oh, that's TOUP, that's the top and the 1-up things, which is in blue. That's why they have a different sprite or a different pattern. Then the copyright sign and the entire alphabet with a dash, a blue dash. Then the C, a flower, a heart, an arrow to the right, and then that's directional water. Yeah, I don't know why these are loaded in here. And then the wall. Yep, that's the wall. Then the grassy thing, that's for the border and the password selection screen. And then, oh, so we have the grassy thing, that's correct. Is it? Yeah, it is correct. And then the next one is a full block. with color alteration, which we can't see, and then it's wrong. This is wrong, because 116 should be this block here, and that is different. Unless I'm looking at the wrong loading, of course. Actually, I should look at it when it breaks on the pointer that we decoded, right? Because this should contain the block. So let's break on the start of the function and see that we have the exact correct pointer. So where does my function start? 6CB8. Okay, and then we will go back to the main menu. Okay, and now we have to look at HL to see whether we have the correct pointer. The correct pointer would be 8B97. We have to add 4000, so 8B97. It's not this one. Not this one. Okay, so it is going to be in the demo then. So we have to wait for the demo. Yeah, okay, so it's the first one when the demo loads. So I have my breakpoint on the exits, or no, I don't. Is it 6CE8? Better double check. 6CE8. Is that a? That's not even a thing. It's a CEA. Okay, it was this return, I think, right? 6CEA. Oh, yeah, of course. Yeah, that's our return. Yeah, so now we can check. I mean, I hope it is though, because we have multiple returns. We could still be looking at something different. Right, no, I was going to look at, well, at the end here, C800. Yeah, we still have the 3s here, which we have different though. So if I let this load into a sprite table, which should the top part should be in now, because this call loads it into the tile into the pattern table. Yeah, it has the blocks here, so I don't know what mistake we're making, which sucks because it's like right in the middle of the data, right? So that's not going to be easy. Yeah, I don't know why this is failing though. And does it restore or? Yeah, so this is then good again. Why are these 4 wrong? Because then we have the diamond framers, and then we have Snaky. That looks like Snaky. Although 132. Yeah. No. I don't think 132 is correct either, right? No, that doesn't look correct. Nor does 133. Nope. There was a third section, right? If we remember, there were 3 sections in the function, and we did implement 2 out of 3. So perhaps it's that, because 133 is definitely not correct. And 134. Also not correct. No. Okay, let's see if we can find that third section again. So from the start we did this part. We jumped out to 6CE2. Which was the second part, I think. That was the block copy, right? With our LDIR here. That's the block copy. And then, so we're doing a non-conditional jump to 6CDA, which is back up, right? We're incrementing, yeah. And then all the way to the top of the function, okay. So where was this jump to? Yeah, we have our LD, so it should be here, right? Yeah, this one, 6D05. This is a jump target that we haven't. Yeah, here, this one. Okay. Oh, we didn't. Yeah, we definitely didn't look at this. We have to check whether A is 0 at this point. If it's non-zero, we have to jump to this routine and do something completely different, and that's going to affect the other the wrong tiles here, the wrong sprites. So where are we here? That is after the. That's just before the block copy. Okay, let's look at the code again. So when we're doing the block copy here. So there's an if here. Let's include this, and then we have to do something else here for some reason. There is a check here. We're loading B into A and testing it for 0. I don't remember what is. Oh, and over here we're loading A into B, so that's the repetition count, I think. We'll have to see what that is. I mean, the problem is the first thing that fails is like way deep, like pattern, like what was it, like 100 and something. That's going to be hard to like get to unless we break on this jump being taken, of course. Yeah, I mean, we can break on 6 DO5 and see if we hit that. Wait, let me remove this so we have the thing for sure. Now we have to restart. Yeah, that seems to be hit quite a bit. I'm going to disable these and then go back to the main menu and re-enable these and wait until the demo plays. Okay, so we are looking at HL now. This is the start of the function, but this is the correct, no, this is the correct pointer, right? 8B97, yes, this is the correct pointer, so we don't have to wait here anymore, I guess. And now we will be hitting 6D05. Yes, so we do hit it in our algorithm, right? That's why it's wrong. Now, where are we here? So did we exchange? Yeah, we exchanged back, so we don't have to look at the primes. We are located at CO20. That's quite early on, though. That's the second line already, and I thought that was correct, though. Well, CO28, so it's this one. That might be wrong. Weird. Okay, so we're loading. So do we have the pointer again? Maybe it's on the stack. 8BB2. Yeah, 8BB2 is this one. This one. So that one, that's the one that triggers the fault. Okay, let me do my output again with the text here. Oops, we have an error. Okay, that's of course incomplete. So we're looking at 04, that we're starting from here, right? So we have to look for DFA104. Current value is the line current value here. DF current value BF. No, I mean there is a DF over here. Actually, we need to look at current except that could be a, yeah, no, I'm going to look for 04. Okay, that doesn't occur. Current value colon OX04 does not occur. Oh, so it's A1 then. Okay, if it's a compound thing. So A2, A1, that's also, yeah, A2 and then A1, yeah, sure. So it's this one, A1, block copy pattern index 4, offset 32. So we are definitely in this code path, which is good, because that's where we have the bug, right? Where we have the extra if clause we have to implement. And the offset is 32, so that's going to be different than, Okay. Right, so A1, the bottom 3 bits are 1, that's probably the A1 here, right? The A register. I have to look at this one too for a better overview. So we are here, and we jumped from here, right? So A contains B and B and tested. Okay, so B and A are indeed the same, which is 1, and B contained this one. That's the repetition count, then I think. Yeah, I think that is the repetition count. I think so. So let's assume it's the repetition count, and then we're loading that back into A. Okay, and testing it. So the repetition count is non-zero, right? Hence we make the jump. Yeah. And then we're loading 8. Okay, so we're immediately overwriting the C register, which we're doing here. Fine, okay. Push the E, we're loading the current byte. So C, oh no. So we're looking at this at the output now. So HL is pointed to CO20, that's the 0, 1, 2, 3, 4, pattern 5, ID 4. Making sense because we have 4 here. Yeah, ID 4. Okay, wait, I think this might be more than one copy. So we're loading the value of HL into A, right? HL, that's in C0, I guess. Yeah. And we're loading A into the counter thing. That's going to be used for this DJ and Z, for this little loop. And we're rotating right. Oh, is this like an invert? It's like this could be a mirroring thing. Because if we, so C0 is the first thing here. or inversion of something. Yeah, wait. So C0, wait, let me get the calculator here. If we do C0, that is, of course, 1, 1, and the rest 0, so only the two top bits are set. But if we rotate this right, wait, no, we only do one rotation to the right, though. Yeah, that becomes, of course, 0110, so we're shifting or rotating the bits to the right. One position. Okay, that becomes 60, sure. And then rotate left of D, which is also C0. Wow, okay. Which becomes 80. And we're doing that 8 times. I have to figure out what the D register contains because that's not being set here. So we're rotating right 8 times and rotating left 8 times. The first in the of the A register and the leftist of the D register. What could that achieve? Oh, right. It's I think it's flipping them horizontally. Because we're keeping track in one way and then we're keeping track in the other way, right? And also we're rotating, so we're pushing, like we're going in a loop, right? We're not shifting, we're rotating. But if we rotate left or right 8 times, do we not end up with the same thing? But I have to make sure that that there are no side effects from this rotation, though, because they have different opcodes here, right? So RRA is, just to be sure, right? The contents of A are rotated right 1 bit. Oh, and the contents of the bit 0 are copied to the carry flag, and the previous contents of the carry flag are copied to bit 7. Okay, so we're rotating over the carry. Okay. But we're doing it 8 times, so I think we're ending up with the same thing, though. And then we have RL. RL of D. The contents of D are rotated left 1 bit position. The contents of bit 7 are copied to the carry flag, and the previous content. Okay, so it's the exact same in the opposite direction. But the carry is in play, though. So we both started with C0, right? So if we do C0 rotated to the right 8 places, we end up, oh no, is this shift or, yeah, this is shift. I don't think I can rotate here. Can we find the calculator for that? So we have a hexadecimal of C0. We want the size 8 bits. We want to shift. No, we don't want to shift. We want to rotate through carry 8 times. Direction is to the right. Right, that's exactly what's happening, right? So, and our end result is okay. So we're chopping off, like 1 bit gets lost in the carry, right? I'm going to peek ahead and see what we do with the results. That's also important. So we are rotating left, right, and left here for 8 times. Oh, and then we're loading D into A. Okay, so why are we rotating A here though? What's the point of that? Wait, oh, wait, no, we have to make sure. So these are not 2 independent operations because they are both executed in the body of the 8 times loop, but they mess with each other's carry, right? Because if this one puts something on the carry flag, this one picks it up. I'm still convinced it's flipping them though. It's mirroring them. Because that might be an operation that you need to do, or like like it's an efficiency thing, right? You have the sprite flip like this, and then you have to do the mirror thing. You only have to store, like you have to say copy this thing, but mirror it or flip it or whatever. So we're doing the rotations. Yeah. So I can't just look at these 2. We have to do 2 at the same time, and taking the carry into account. This is going to be hard to implement in C++ though, because we don't have the rotate thing available. That's gonna suck. So, but why? I mean, yeah, sure. That's the reason why we are doing this here is just because we're overwriting A here with D. Doesn't mean that we're not using the rotation here because of the carry flag, right? So then we're loading that into A, popping DE again, and then rotating. Okay, and we're writing that out. Okay, sure. And then here's our second loop. So we're doing this for every byte because we're initializing C to 8, and then we're jumping to 6007. Okay, and then so we're doing this. These are 2 nested loops, right? I think we're flipping every byte and doing that for every byte. And then if that is done, we're jumping to 6002, which is the end of the thing. And then this is something else, I think. Yeah, this might be a different function. Does this, is this being called anywhere? Oh, okay. The 2 decoding routines are right underneath each other or next to each other. Okay. Yeah, this is the function below. So these 2 decoding functions are right on top of each other. Yeah, this is the end of the function. Okay, that's good. That means we have everything, right? We know all the parts now. So this has to be either inverted or flipped. Let's look at the result. It's as simple as that, right? Instead of guessing. Because if it is a simple flip or mirror or whatever, then we can do that with our own algorithm. We don't have to do the rotations because they're not available, right? So where do we see the result? No, wait, I want to see where we get the result. That would be here, right? At this point, everything will be written. Yeah, let's stop at 6018. We are dealing with index 4, because that's this 4 here. Where are we? Yeah, this 4 means the 4th pattern index. And if we look, we are copying these 8 guys. That's the source, and I'm assuming that we're going to overwrite them here. So let's see what that becomes. I assume that these 1820s are going to be overwritten now. If I continue. Yes, they actually are. So actually now I just have to see what pattern 4 and 5 are, right? It's the strange thing is that I didn't see here in my output how they were wrong, or how they weren't wrong. Yeah, we're starting at 0, so it's 4 and 5. Oh, right, so 4 and 5 are identical here, and I'm assuming, yeah, this is the bridge, right? So these two patterns are the little bridge, and the 5 should be mirrored, I think. So let's see, let's continue. I don't think we have to go through the assembly anymore, because it does make sense. Let me turn off the breakpoints here. These guys. And now if you go look at the tiles here, let's pause the game. Yeah, so these two here, pattern 4 and 5, these are flipped, right? Horizontal flip. But in my output here, they aren't. And that's the only thing. So that's what we have to do. Yeah. We only have to figure out the condition when to flip. But yeah, this is the thing. I didn't see this. I overlooked this, but yeah. Because over here they're clearly flipped, right? So let's try to implement that. We just have to figure out the condition on when to do that. So if we go look at the code that we have, yeah, it's this if clause, right? I mean, I can just, it doesn't matter which one is where, I can always flip them around, but I need to know when to do the flip. I have to find out where that exactly was. So it's this jump, I think that's the first. Yeah. No, that's yeah, 6 CEB. Those are our two conditions to do a block transfer. 6 CEB starts with our block transfer here, but there should be a condition here. So yeah, we have to calculate the starting position first. That's what we're doing here, right? We're calculating our starting position of the sprites in the output array, and then this is the condition, I think, because over here we're doing a block transfer, and in 6D05 we are doing the flipping and then the writing. So the test, this is the test. So it is being determined on what B contains at that point in time. And B is, I think, the repetition count, because that's this one here. Yeah, so A is still in the thing here. And we are jumping here from here. A is untouched, C is in A and is inverted and ANDed. Okay, right, that is, I think, yeah, it's the inversion and the subtraction that was our repetition count, right? The inversion and the ANDing, no. So it's the repetition count. I mean, it is not a repetition count anymore, of course, but I think if it means if repetition count not equals 0 or equals 0, then we do the block transfer, and else we do a flip. So actually, considering we have this algorithm here, I think we can just flip it around, right? Oh, no, we have to affect this value here. So how do we flip that? I mean, I can do this very inefficiently by just typing out all the 8 things we have to do, though, but that's not super efficient. So we have a byte here, and we need to, wait, let me think. I'm just gonna write it out. I mean, we can, obviously the way to do that is with the 2 rotations, like as they do in the code. But seeing as we don't have rotations, I'm gonna do this the dumb way. So if we say we OR this with right, so bit 0 has to end up in position 7, right? I'm going to do it, I mean, very stupidly, if C and 1 equals 1, then we will, is this going to format? Yeah, do I have Clang format on? And then we have our output, or D, I guess. D or equals second bit, so bit 2 has to be in position 6, right? Is that the thing? I mean, this is stupid, of course, but I don't really care. Actually, I'm not going to do this in hex. Then I don't have to think, or I have to think even less. No, wait, I'm being stupid here. 1, 2, 4, 8, 16, 32, 64. Yeah, no, that's correct, right? 8, 16, 32, 64. We're missing one, right? Okay, I have to do 8 positions, I guess. No. Well, okay, no. So what's 4 and 5? So we're definitely making a mistake here. Yeah, this is wrong. What am I doing wrong? So if the first bit is set, we're ORing with 1 shifted 8 position to the left. I mean, this is correct, right? Okay, slow. 1, 8 positions to the left is, oh, no, that's wrong. No, it is 7. Okay, sure. Yeah. I don't know, maybe this is not necessary. So wait, so C and, so let's say, let's take FF, of course, and 64. No, not 64, of course. That's decimal. And what is that? 40? Yeah. So 64 is the 7th bit. Oh, it's 127 then, I guess. No, it's 128. Again, working in decimal. So yeah, 128. That needs to become bit 1. Why am I making a stupid mistake here? So we're flipping bit 1, 1, 2, 4, 8, 16, 32, 64. So if the first bit is set, we need to do 1 shifted 7 positions, right? That does make sense. 1 shifted 7 positions to the left equals, yeah, that's correct. So, and then 2 is 1 shifted to the left 6 times. Yeah, that's correct. 2, 4 becomes 5 positions, 8, 4 positions. So is that still correct? Like 1, 8 would be 4 positions to the left. Yeah. Oh, wait, no. I'm not rotating, I think. No. No, yeah, I am. Okay, so 8 is correct. Why am I running out of values here? Oh, is it just... Like if we do 128, oh no, it is correct. Like, well, that is the last bit. I don't know why I did that wrong, but yeah, that's correct. Yeah, I don't know why I did that, why I was confused about that. So very inefficient, but who cares? But now it is flipped. So pattern 5 is now flipped. And we should end up with those 3s at the end. Yeah. See, these 3s, we didn't have these 3s, and that now makes sense. Okay. So we started to fail at position at like the block, right? Where are we in the code here? I think we can, okay, no. Like, let's look at this again, tile viewer. Yeah, pattern 116 was incorrect, right? I don't know if it's going to be correct now. I need my output. Already forgot the number, 116, yes. I'm not sure though, like, I need to, I shouldn't let the game run. I need to inspect the pattern table at the time of the return of the function. Because there might something might have like overwritten, because there's multiple times that this thing gets triggered though. No, I don't want you to break yet. I'm going to let you break at these 3 positions when the demo plays. Okay, so HL is CO20, that's not correct. Okay, no, not you yet, I don't care about you. That's also not interesting. So 908F, that wasn't it, right? No. Oh, was I? Oh, no, it's the other way around. It's the... Yeah, it's the one that when the menu loads, that's the one we need. I keep forgetting. Okay, so it's this one. Yeah, Right, so 115 was the problematic pattern, no, 116. So if we do look up where that is in memory, that would be 116 times 8. Let's convert that to hex and then add C000 is of course C3A0. That would be this pattern here, this one. Okay, now I have to look that up. I mean, it's going to be different here too, of course. Yeah, I mean, finding that is going to be hard. I mean, I see 4 F1s here in a row. These should be easily found. Okay, this is more difficult than I thought. Why can't I see these? We're correct, right? Yes. Okay, these are the 4 zeros. Oh yes, it's the 4 zeros here. Okay, yeah. E0, no, these are different though. What is this? Okay, now I have an entire thing of zeros here. Okay, that's perhaps this one, 5F, 4F. Why does this look so different? This is impossible. We're not looking at the same data. Why? Oh, I didn't check whether we're loading the correct offset. Of course, I didn't break on the start of the function. Of course, which I always forget where that is. That's at 6CB8, which I haven't got in my thing anymore. 6CB8. Right, so I need to have the correct data set, of course. No, crap, I needed to go to the demo, of course. But this will work too. 8B97. Okay, so this is the code for sure. So let's make sure we have the correct. So this should be the return, right? Okay, so what data do we have now? 2 sets of zeros, 1, 3, 3C, okay, 3E. Okay, so this should be more correct then, okay. And then our offset was C3A0. Yeah, okay, that's different indeed. So we have like a bunch of zeros. That's this area, I think. Yeah, EF, EF, EF. And then the next two is, yeah, it's this one, which is identical. Okay. So I am decoding it correctly though. Like if that's the pattern, like this section from 8E8 to these C zeros, these are identical, right? 8A, AA, FFs all the way. 0, 80, C zeros. 103, yep, C zeros. 80. So okay, so pattern 115 is definitely going to be in that area. That means that if I return from this function, I think that block won't be there. So I'm going, because it has written it here, but I don't think it has written it to the VRAM yet. So let's continue here and let it write it. Yeah, so these 3 calls are going to write that into memory, right? So let's look at the tile viewer here. I hope this overwrites this immediately. I don't want a tile. So yeah, let's do this call. Okay, so yes, we have pixel data, but no color data yet. That is fine. And pattern 150, yeah, 16 and 17 it was. So yes, this is not incorrect. If you go look at pattern 115 and 16, at this point in time, it contains this, right? This little thing at the side here. And that's exactly what we're seeing in pattern 116. So it's overwriting this data with other source data. That's why I'm getting a different result if I look in-game. But yeah, so these are correct. We have 116, 117 to the right, 118, that thing. I don't know what that represents though, but sure. And then 120 is back again. Yeah. So that means that our decoding routine is entirely correct, right? Wait, these look weird too. 132. Crap. Why is this different? 132 should be the same as 134, right? No, why are these different? How is that possible? So 132 should be snaky. That's the top of snaky looking to the left. And that's completely gone now. I don't understand. 132, I keep closing my calculator here. 132 times 8, come on, is 1056, in hex is 420, so we're looking at C420, that's this line. And now let's look at the output, C420. Well, I don't have the address here, but we have a couple, so where are we? Around the middle, right? Yeah. So we have a couple 70s. We have 4 zeros here. Where do we see 4 zeros? Oh, 119, 31, 70s. Okay, and then the next one. Oh, yeah, this is different. This is indeed different. This should be 6C, 16E, 1E and stuff. And this is, both these are completely wrong. And the next one too, 5D, 63. Okay, it looks like we're skipping something here. Yeah, because I think things are messing up from this point onwards. Because nothing, well, the one, it does. It is okay again. Yeah, OP. At this point, it's okay again, but everything between this and this is wrong. How can that be so wrong? We have to figure out which byte that is represented by, of course. That's not going to be easy. I don't understand, how could these be so wrong though? Can't remember the number already. 132. Yeah, these don't make sense, and it does fix itself after a while. Yeah, this looks correct. This is call facing right. This is called stale. Yeah. So what's up with that though? Why is that being wrong now? Let's look at the code, see if I made a stupid mistake here. Also, we can output data about that too though. So I'm gonna comment this out. We don't need that. I need the pattern counter though. That would be handy if I know where we are in the sequence when outputting this. Can we determine that? Wait, where do I assign here? But I don't know the. Yeah, no, this repetition count can. I mean, I'm assuming it's going to be within the 8 bytes. Like it's doing chunks of 8. But that's not guaranteed, of course. So it could go beyond the boundary. I mean, I doubt it would do that, but because they have the block copy specifically for that, right? So why would he go beyond the boundary? But that means I can't put an index when I'm dumping this text here. It would be interesting to know. Actually, if I do put this one out here, yeah, maybe I can do it like this. Then I at least can look at the position, right? And I'm going to add C000 so I can have the same number in the memory view here. That would be easier. Yeah. So C420 is what we are looking at. Why are we not adding C00? Oh, did a mistake happen? No. Of course, I did the wrong thing. It's this one, of course. It was C420. C4. Ooh. C41F. Yeah, the next one is C420, right? So yeah, okay. So I'm only doing the writing part. I need to block copy as well. So block copy pattern index. This offset. What does offset mean? Offset is offset here, meaning that's the byte offset within. But that's going to be correct though. That's just the current value times like times 2 times 2 times 2. That's fine. We don't need that. What we need is pattern index to this position. C420. C4, yeah, it's this one here. This one is failing because we're having a negative number here. That's going to be the cause, right? So we're doing 4 block copies. It was more than 4 that were wrong, right? 1, 2, 3, 4. Yeah, this one was wrong. C440 was also wrong, I think. Was it? Oh yeah. Wait. No, I mean, was that correct or not? 6C, 1C. Let's go look. I have to find it again. The 4 zeros. Yeah, this one maybe. No. Oh, no, it was. And then the 70s, yeah, and then this line is wrong. This line is wrong, and then 6C, 16. Oh yeah, no, it is indeed these 2 lines. So there's 4 that are wrong. 60, 16, 1E. Yeah, this one is correct again. So there's only 4 wrong. No. Wait, 6016 1E. Oh yeah, that's the one that's correct. And then 2 lines above, and then the 70s are correct again. EE, F0, FC, F8. Yeah, okay, so it's these 2 lines. So C420 and C430 are wrong. And that's exactly what we see here. Those are 4 block copies. These probably also wrong, because this has a negative number too. C420 and 30. Yeah, index. So there's the index is wrong. The pattern index is wrong. Okay, let's go look again at that. So this is the times 2 times 2 times 2, right? We're loading A in the bottom part of HL and 0 in the top part of HL, meaning it's just the value itself, and that is the current value. So what I need to know is what is... Oh wait, is this an... Okay, let's do this. Let's differentiate between these two. This is the normal, right? Yeah, this is the normal one, and this is the mirrored one. So we know where exactly is the mistake. In which of the 2 paths? C420. Yeah, okay, within the mirrored thing. So pattern index is wrong. So, I mean, I need to... Where do I pick up this this pattern index though? Okay, can we get rid of this shit here? Apparently not. I'm not using current value anymore, and that worries me because we need that. So pattern index. Oh yeah, that's because of the offsets. Okay, sure. Oh, we're overflowing. So this is a signed integer, right? Yeah. Okay, let's make this an unsigned integer, and that might fix it already. Apparently not. C420. Well, I mean, the output is still, yeah, because I'm using current value. Wait, so that I can't rely on this standard output here. I have to look in the data itself, right? So C4, so we're looking for the 4 zeros again. I thought I had them, but I lost them. C7, C3 above. Wait, are we completely broken? No, we're not, right? Yeah, C7, C3. Okay, but it is wrong though, because I'm seeing I'm not seeing my zeros here. C1, C0, E0, 7F3, F0. Okay, that's correct. Except this one is not correct now, and more is wrong now. Okay. Yeah, what did I change? Oh, I changed the signness of the thing. So offset. I mean, does it not automatically? Is it messing with me? Is it casting at the end wrong then? Of course, I can't look in this one. I have to again search for these zeros, which I wouldn't have found because there were no zeros anymore. The one that was correct was 770F. Which now isn't in there anymore either. 6C. Oh no, that was. I'm looking for 7077. Okay. Okay, 3H, 3F, 3F, 1F, 107, EE, F0, FC, that's again correct. But then 6C is incorrect, we have zeros now. Again, these two guys for 20 and for 30 are completely broken. And for 40 is 6C, 16. Why, yeah, this again. Yeah, these four are still not good. We know now who they are here. Okay, where are they? Here, these guys. Okay, so I do need to offset then. Okay, so let's make the pattern index thing a unsigned thing. Okay, why not? And the same for this one. So we don't have the negative sign over there, at least in the stupid output. Actually, let me just ignore these guys, because we're not looking at arbitrarily lengthed outputs. C420, yeah, it's these guys. Okay, so these do make sense though. We're copying 129 and 128 and 131 and 130. Wait, let me see. Does this make sense? So our pattern that was wrong was C4 30 and 20, right? So 20, 21, 30 and 31. So C4 20 is, if we do that to decimal and divide by 8, that's pattern 132, of course. Yeah, of course, that's the inverse of what we did. So we are writing 132 and we are inverting 129. So 32, 31, 30, 29. So that would be this one inverted then, I guess. Okay, and we're doing that. Okay, sure. So that might be okay though. I mean, I say that. Now the question is, are the other ones also incorrect though? Well, no, because we looked at the thing here. This one was correct, right? So. Yeah, these are flipped and they don't need to be flipped. And there's definitely not a 2 and a 1 there. So we are accessing the wrong pattern index, I think, that we have to flip. And current value is at that point. Oh, do we perhaps need to cut off some something like hand off some value? Because if we look here, so we have our times 2 times 2 times 2 coming from A here. We jumped here, right? So we're loading A into B, and the no, this is actually the value, right? This is literally the value of the thing. So actually, we should be able to see that it says 132, right? That is 84. We should see that in the data here somewhere. I mean, good luck finding that, but and it should say 84. Oh no, that's the value. I don't know what the preceding number would be. Okay. So we have our ROM here. I opened it in the wrong application though, but because this one sucks. We need to find our starting point was this one, 8B97, but let's just go to, well, it's 4B97 then, right? 4B97, can we go to? Nope. 4B97. Oh, with these applications, I don't know why I opened it in this one, it sucks. Can we go here, jump to 4B97, starts at F8. Oh, for C, for B97, yeah, it's this one, right? So from this point on, we should find a 84. I hope this, oh yeah, it says from cursor, X84 for FA0. That's 8FA0, that's quite far down. Yeah, it would be this one. So FE84. I think it might be this one, although that seems quite far. Well, so FE, if we look at FE as our first byte, what do? We AND it with a prefix 1. I mean, it's not gonna happen. It's definitely gonna end up in our block copy thing though. So this is gonna be true. What's also weird is that Oh no, I was gonna say that we don't use the inverted part, but yeah, we invert it here, and the prefix one, I mean. And for a one repetition, we do use the regular one. Okay. Still not sure why these values are actually relevant, but sure. Right, so we're jumping here, 6 CEP from here or from here, but that doesn't affect the things here. A is already set here, but we are loading HL into A though, so that's literally the byte. That's literally the data byte being 84, as in the pattern index. Okay, I did load them in, right? So I can see if others are flipped. So if you look at the output again, I wonder, like 134, well, those were definitely wrong, right? 134. Yeah, that should be something completely different. That's the butt of a gull or a snaky, perhaps. And 134 and 135, 136. That seems to be correct, though. Yeah, that is correct. I mean, the blocks in my output aren't square, so it looks a bit different, but that does seem to be correct. Also, they seem to be inverted, but that's just the colors over here. Right, that's fine. Right, I need another another mirrored block copy one. So pattern index 96. Okay, there's the arrow pointing towards the top in the bottom right corner. Pattern 96. Yeah. Yeah, that is correct though. So the mirroring does work, but not for all of them apparently. Unless, so pattern 96, I said, that's still below 128 though. So, oh well, no, I'm using 96 as the source. I don't have the target here. I can't determine the target at this point because I don't know where we are. Well, to C308. Oh yeah, no, we can just divide by 8, right? Yeah. Yes. So block copy mirrored pattern index to pattern index this, and this would be current output index over 8. I think that's correct, right? Because we know we are dealing with a an entire pattern, so 8 bytes. So yeah. So we know what we're copying to where. So I was looking at 96. Yeah, that gets copied to 97. So we'll have to look at 97. So 96 is a source. So of course that's going to be correct. It's going to be 97 here. So yeah, so these are indeed horizontally mirrored. The question is it the same or is it correct in my output here? So 96. Yeah, that is. So it's these two here. That's on the right and that's on the left. So these are correct. So it's definitely doing correct, but 96 and 97 are below 128. So perhaps it is a signed thing, signed, unsigned problem. So let's pick one that's above 128. So copying 156 to 157, all right, 156, 156 to 157. Okay, these are indeed mirrored horizontally, 156. Yeah, That's these two. That's perfect. That's these two. I don't understand what is wrong with those four guys. Yeah, that's the skull, Medusa. That's the egg, the broken egg, the respawn thing. Yeah, that's the disc icon, the tape icon and the disc icon. Yeah, so it was 132, right? Yeah, 132. Okay, 132 is correct now, though. Why is it now correct? 131, 130. Yeah, that's correct now. And I didn't change anything. Yeah, 129 is snaky facing to the right. That's this one here. Then we have 130. That's this one, yeah. 31 is, I think, the bottom right of snaky facing to the right. And then 132 is the top left, or the top part of snaky facing left. Or was it 128? What is 128? Yeah, no, that's snaky's head. Okay, now the error is gone, and I don't know what I changed. Or was it these guys? No. 160. Nope. I don't know. What did I change? Other than the signed change? And this I changed too. Okay, so that means that my output, wait, so we remember C20, C420 and C30 were wrong, right? So these guys here, so they're supposed to be right now then. So we have to find our 4 zeros here. These guys, and then we have 70s underneath, and then 6C, 6. Okay, so that's these two lines. Now they are magically correct. 1E7FC9, wait, what? 6C, no, it's this one. 6C16, 1E7F, E7, F3, F3, E7, yep, that's correct. What is this nonsense? Yeah, now they're correct. No clue. That's so weird. Because unless it is this, oh wait, did I? Well, I messed with that, but that's just the output of the thing, right? So I messed with that. I messed with okay, so I did put this in auto, but that is the same thing. Okay, so let's compile like this then. Pattern 132. That's correct. Yep, those are correct. So, I mean, that can't be the thing, right? I mean, that's just the auto that can't make a difference. And that's putting the text away. Yeah, I don't understand. I don't know why, but I'm not going to complain. Okay, and those 4 last ones are empty, yes. And then 251 is just that. Okay, so it looks like we have them all. Now, I guess the next thing is the color information that we would have to add. But we have to find where that is though. So at this point in time, we don't have color information in the emulator either. So I'm assuming that the next call to this function contains the data for the color, the current color pattern, right? The color information for this set of tiles. Tile sets at menu load, and I'm assuming that the next one, and we're going to find out the offset then, which we then can decode. So we have to break at the next call of this function. The start of the function was at, always forget this, that's 6CB8. All right, so let's continue. Yeah, and we do, oh crap, so we break, but the color information is already here, so we skipped it, meaning it's a different function. Crap. Yeah, it's already here. So if you look now, we're loading 9287. 9287, that's like this guy here, this one. It's another set of data. Well, we can dump it though. 9287. Let's just dump that. And let's see what that contains. This might not be pixel data, so we'll have to, I'm dumping it as pixel data now, but let's see what it gives. Yeah, this, well, maybe. This, yeah, this does look like valid stuff though, is it? That's Lolo, right? Or Llama, perhaps. Go to the end of the function and see where this information is being dumped. That's 6CEA, I assume, yes. I'm going to go there. So we have all this data at C000, I assume. Yeah, to C700, that's less information than previously. But let's see if it matches what we have here, right? So OF is our start. These do look like recognizable things though. Maybe, yeah, that's Alma. And that's skull. It starts with a skull for some reason. So OF3, F7, yes, that's correctly decoded. It looks like at first glance, and indeed 700 hex bytes, which is what we see at the end pointer here. Like C700 is the end. Yeah, so 1010A or 1010A0 is 0. That's perfect. So we have that down. Only we don't know where that gets written. Well, we do if we continue the execution here outside of this function, because this function only decodes, right? So we're loading C000. Okay, so this is going at position 3800, and now, like, presumably also in VRAM, so that is graphical data, but we have to look up what that address represents. 3800. Let's see if we can find it in the registers. Yeah, sprite. Oh, okay. These are the sprites. Okay. So the previous ones were tiles, right? Yeah. These are sprites pattern tables. So we have the regular pattern table, which is this one, which is at 0, and then we have the sprite pattern table at 3800. Okay. So this is that's easy, but I'm assuming, okay, so, well, we can go look to, now that we know that it's sprites, we go look in the sprite viewer, and they will be loaded in as soon as I load this call here. I'm assuming that this call will load them in. Yes, indeed it does. And that's indeed the sprites that we've seen, right? Yeah, so it starts with the skull at the open mouth skull. And then we have the eyes. These are the eyes of the skull. And then the fireballs. Yes. And we have Lolo in there too. At pattern 152. Now this is walking Lolo 152 and 15. Wait, 152, 156. Okay, so they skip a few. Okay, 152. So that's 152, 3, 4, 5, I guess. 152. Yeah, 152. That's Lolo. Yeah, that's the 4 things that make up Lolo. So in fact, actually, I should make a dump sprite routine that groups them by 4. Let's do that quickly. That shouldn't be too difficult. Yeah, we need to pass a function or a parameter that says how to group them, though. Print pattern, that should be called print tile. And because that does a tile, which is an 8 by 8, and then we will do a print sprite, which does a, oh wait, will that work? Yeah, I don't know if that will work though. They might be, like the 4 quadrants might be in the wrong order. I might have to do something more in detail or more, I don't think it comes down to doing this. I doubt. So oh yeah, we're doing 1, 2. Okay, no, I have to do it like this then. No. Why is my, oh, okay, my formatting is off because I don't have a configuration file, so it puts the case on the same line stupidly. Yeah, I can't do this divided by 4, right? What is that, 64? Print sprites, because these wait, how does this work? Pattern index times 8 plus I. Yeah, this might work though. So this should be a sprite index, and then yeah, that runs from 1 or from 0 to 63, right? Yeah, but I need to, this is wrong too, I think. Pattern index, it's times 4, right? Times 4 times 8, because I have to multiply here as well, I think. I'm not sure. Is that correct? Yeah, because you're asking for sprite 2. Sprite 2 is patterns 4, 5, 6, and 7, starting from 0, right? So sprite 1 is 0, 1, 2, 3, and now 4, 5, 6, 7. Okay, so we're entering 1 for sprite 1. 1 times 4 times 8. Yeah, because we're doing bytes, of course. So 1 times 4 is 4 times 8. Yeah, I think that's correct. Not sure though. And then we'll do output type sprite, and this is output type tile. Let's see if that gives us something different here. Yeah, as I figured, it's not like the offset is wrong. Or are we not doing enough? 64. Oh, 16 needs to be 32, I think. In our print sprite thing. Yeah, this has to be 32, right? No. No. I mean, this isn't super important, of course, because we do have the information. Okay, let me output this as a tile again, so I can see how they are arranged in memory. Yeah, we need to put this one in the first position. Oh, and then this one has to go underneath. Yeah, that's what I figured. So I can't just put 0, 1, 2, 3. I can't do that, right? I need to do them 0, 1, 2, 3. Like my indexing is incorrect here. Right, so the order we have to do is, so 0, we can start with 0. That has to be top left corner. Let's just write it out like we, as if we are doing tiles, right? So we start with the first one, and then we need to do the same thing. Wait, I and j are, I need to know my x's and y's at this point because, right, let's do this. This is gonna mangle everything up, I think. Oh no, I need to do print sprite. Yeah, I think this will mangle everything up. Well, no, it doesn't. But I need to go farther. Yeah, why is this not working then? So, oh wait. I mean, the order has to be the same though, because that's how the game loads it, right? Why are they shifted to the right? Oh, I am doing reverse order though. That's probably the issue here. Oh no, these, oh wait, no. There are only 8 bits in a byte. Why am I doing this? No. This has to be 8. This has to be 8. Right, and we're doing 16, so we have to do the width. The width is wrong, right? Yeah, of course, this is the bit set. Why am I changing this? We're looping every bit within 1 byte. So this is a row of... Do we need to go to 32 here then? No, because what we do need to enter though, as in we have to put a new line in things. Yeah, so then the new line is here. It is correct, but the new line is here. I shouldn't do the new line yet. I need to do the new line after. Yeah, of course now it puts everything on a thing, right? I mean, of course I can do it like this. If I do this twice, not good. Okay, why are we messing up? Why would this not be correct in the half of them? Why would that not be? That's so weird. Why is it not outputting the new line? I mean, it is outputting the new line, but surely, I mean, it can't be 7, right? So we're doing this 32 times, right? So there's 32 bytes. Oh no, of course. Yeah. So they are in the wrong order. Yeah. The segments, the quarters are the quadrants are in the wrong order, right? Because if I like, yeah. Yeah, so I'm doing, we're talking about rows here, not columns, of course. Yeah, I'm gonna have to do the quadrants separately, I think. So yeah, these are rows. I was thinking these were columns, that's why I was mistaken. So if I do 16, I get half the skull, right? At the top, I mean. Right, so yeah, so, but that's not good. I need to do 8. So I have the top left part of the skull. And before we do the enter, we need to do this thing too. We need to do this twice with a different sprite index. We'll put that in a loop later as soon as I figure out how many we have to add. So we have to add how many do we have to skip? I might have to guess here though. So an 8x8, 64 then, I guess. No, we have an error here. Okay, we're redeclaring, that's fine. We'll put that in the loop in a bit anyway, if we can figure out. Okay, no, that's wrong, so that's too much, right? So that's the same quadrant. Okay, we're still far away. Okay, we're still too far away. Okay, sure. So this is the wrong one. Yeah, okay, that's the bottom one. So it's 16 then, right? I think that's the top right quadrant. Yeah. And then we need to do the bottom quadrant, which is at, no, that's going to be 24, I assume. Oh no, now we have to do the new line. Okay, sure. I mean, this is going to be 32 then, right? Nope. Of course, this is wrong. Why is this so wrong suddenly? Okay, let's wait with this one. Wait, why are we suddenly so wrong? Oh no. We don't have to do that here. Yeah. Wait. We need to do two of these guys. Yeah. I think we do have to do it like this, and then this becomes plus 24, and this becomes plus 32. Except they are switched, they're swapped. Okay, no, it's too far. Why is this so wrong? Yeah, the first one was with the mouth open, right? Okay, I'm one too far though. Yeah, so this one on the left has to come to the right. So that's definitely that one then. I'm gonna do the same here. Yeah, that's the open skull on the right, and then this one has to be, so we have 8, 16, 32 then, I guess. Well, no, that's wrong, right? Yeah, that's too much. Wait, is it 8? Of course. Okay, that took a while. Right, so these are the sprites. That does make more sense. And these all look correct though. Yeah, those are the eyeballs. That's low. All right. So we have these guys, and now we're still missing the color table for this one too, right? So this one doesn't have a color table, I think. Well, I don't know, it should have. It should have. Yeah, but we have to figure out where that information is stored. I assume they would have used the same function for that, the decoding function, but apparently not. And we did figure it out already though, because we did see that last time. I don't know why it's like, when we looked at this last time, we saw, yeah, here. So, oh, like it's the other algorithm. Okay, it's the artwork, is the, yeah, it might be the other function, the artwork function that does the decoding of the color table data. Which is fine, I guess, because we do have that information too, right? Now all that's left is just exporting that information, I guess, and then we can start working with this, converting it to whatever we want, right? Right, so to confirm, it's going to be this one, 7585 plus 4000 or minus 4000x, plus, I think, yeah, plus 4000. Yeah, let's look at that function. Let's see, no, not this file, this file. Like if we stop at 61A, we should be able to see where the color data gets loaded, 61A. Of course, I have to get the correct pointer now, because there's multiple pointers that use this data, and the pointer is 585 at the end, so this plus 4 is, well, 585 at the end. Yeah, B585, this is the one, color table data. So if you go to the end of this function, or our exit point, I mean, 6D29, right, it's still here. So if you wait here, then we can look at C000, and that should be the color data for our tiles. Well, I mean, wait, so do we have color data in the tiles yet now? Yeah, it looks like we do. So I'm going to reset, and I'm going to wait. Okay, so we have the tiles are loaded, right? That's the other call. That's the first call here. Yeah, that's this one. This loads the tiles, and then this loads the color table data, which is going to be written in C000 here. If I continue once to the end of this function, right? Okay, so that's this data indeed. I mean, I should get the sprite color data out of it too, so I have to figure out where that is too, because I don't think it's one of these. Well, it could be though. So this is the color table data for the tiles, and there has to be another one for the sprites. Because like if we look here, so pattern 0 is just empty. Our colors are black and, well, like if I make it 1F, then the first row should be colored differently, right? Or I mean, I can do 4, 4, 5 or 5, 4 for 2 different colors for the first row. So that should work, I think, right? Yeah. So the first row, now the 4 is applied, as in the 4 is blue, right? but because it's all bits are set in that thing, the 5 color isn't used, of course. I mean, I guess we can look at C000 to see where this sprite color table gets written, but I would have assumed that it is the same one of these two functions though that handles that. Actually, yeah. Let's see if we. So, do we have a sprite table already? Yeah. So it might be loaded. So it might be this one, 97D8, unless I've already determined 977D8. Yeah, that's something in game. This might be the sprite color table. Right. So what do we have here? Yeah, I don't know what that is or what that represents. No, I didn't want to merge those. And the length is, it goes until C5, C0, so that's quite a bit. It goes until here. I mean, this looks like color data, but at the top, not really. So, I mean, if this lights up in color, I don't know if these get colored though. Oh yeah, we can see where it gets written to. So C14, oh wait, and it starts at C140. Okay, that's why I was confused, because this didn't look like color data at starting at C000. That does look like color data, but we're starting at C140. So this is the color data, I assume. So we're loading this in C780 for a length of 80 hex only though. That's weird. And we're doing 3 passes, so it looks like it is tile related. Okay, yes, these guys changed. So we're updating like some color data for these. These are the kings, as they call them, right? And then we're going to do the same. Okay, we're going to do the same. Oh yeah, no, it's replacing these icons, the icons for the disc and the tape. It's replacing these with the king things, with the king sprites or tiles. It's weird though, it's doing 2 at the same time. So these are going to change, right? These 4, I think, are going to change. Yeah, oh, and it is doing the white ones as well. And I guess these guys too. Okay, sure. So it's doing the entire row here. And then the third one too. Right. Now what's interesting though is that the color information is already there. And that surprises me, because unless these are, oh no, these might be incorrectly colored. Yeah, because this is the color of the, right, the color information is incorrect because this is the tape icon or the disc icon, and this is the other one, the tape or disc icon. So the colors are clearly wrong, right? Yeah. So now this is going to load the correct color data. So this block, this call here, yeah. So now the colors are going to correct here for these 8 tiles. Yeah, exactly. Yeah. Yeah, and I will do that 3 times, of course, in the second row or in the second section and the third section. Yep, and that's the third, and that's it. Well, I mean, it's not doing it for the third one. Oh, did I go in? No, but now it's gonna, yeah, okay. Okay, so this is just replacing over the disk tape icon, etc. I mean, I guess I don't really need the sprites. Well, I do though, because I need to know where in the ROM they are. But yeah, like I continue, the sprites are empty now. Let's load the sprites. Yeah, that's weird. Okay, I didn't want to do that, but sure, we'll go in-game. And we messed up. I mean, oh no, that's just because I broke. Okay, sure. No sprites here, those are all tiles, that's fine. But now we should see sprites, right? Yeah, okay, it loads a sprite table. Okay, stop flickering. Okay, it won't. So like these attributes are switching between 2 pointers here, right? I don't know exactly why that is the case, but that doesn't really matter. But I mean, I don't think they will assign the colors dynamically though. So we have our okay, sure. So we do have our pattern table and our attribute table. So let's go look at 1B00. So it switches between 1B00 and 1B80. So I'm assuming that the colors are also in there. So that would be in the VRAM at 1B00. Yeah, so 1B00 and 1B80, right? Now I have to look up what these attributes mean. Well, I mean, I guess we can do that really quickly if we can find it. So, all right. This we have seen, right? We have the X and Y coordinates, the character number, and the color code. Yeah. So yes, YX pattern and color code. Yeah, we've seen that indeed. So that just means that Lolo should be moving around here. Yeah. So I mean, the X and Y positions are in here along with the color, right? Yeah. So I'm assuming this is 84 is 132. Yeah, pattern 132. Okay, sure. Yeah, pattern 132 is going to be here, right? Yeah. Pattern 132. Yeah, that's Lolo standing facing left. Yeah, and X is 16 and Y is 7. That's indeed these 7 and this hex 10. And then that's the thing, and that's the color then, OF. Yeah, so these colors are defined by the game, like in game then. I mean, I guess we can get away with just the tile colors, though, the tile color set, if you want to extract all the thing, because all the sprites are also in the tile set, right? Yeah. Although, maybe this one, do we have that Lolo in the tiles? I'm not sure. I mean, I guess we can look in the game itself. Yeah, we have Lolo, but we don't have a dead Lolo. So not all that information is in this tile set. So we do need to figure out how where the information for the colors are stored for the sprite colors. That sucks though, because that can be spread out over the entire ROM. I mean, I can figure it out, of course. Like, that's not a big deal. I can just because, I mean, we know what color it is, right? So it's switching between sprite 2 and 27. I don't know why it's doing that though. Like, it does the flipping between the attribute tables here, I assume. So this one, like if you see sprite 27 here in the thing, switches between 2 and 27, which is indeed this one and this one. But I don't know why it's doing that. So if I think it also switches between pattern 209. Yeah, it's pattern 209 and 132, right? 132 and 209. Yeah, that's impossible. Because that's not an divisible by 8 number or 4. That's weird. All right, so the next thing that we're going to do then next time is going to be the conversion of this data along with, well, not the sprites, but the tiles at least, along with the color data to like a JSON file, and then we can work with that and see how that goes. And I guess we can make a spreadsheet of this as well. But it would be handy if we had the color information for this data, which we don't. I mean, that's fine though. We can figure it out. Okay, well, that's going to be it. I will be back maybe the day after tomorrow, not sure. But yeah, thanks for watching, and I hope to see you soon again.